What if black holes have no center? Imagine peering into the abyss of one of the universe's most enigmatic entities, a black hole, a region so dense and so powerful that not even light can escape its grasp. For decades, scientists held a singular vision. At the heart of each black hole lies a singularity, a single infinitesimal point where gravity crushes matter into infinite density and time itself seems to pause. But what if that long-held belief is not the full story? What if black holes defy the very idea of a center? Could the core of a black hole instead be a dynamic gateway, a place where space-time loops upon itself, or perhaps a bridge to a hidden universe, bouncing energy and matter across dimensions beyond our comprehension? If black holes indeed lack a central point, the singularity becomes an even more mysterious concept. In physics, a singularity is a region where gravitational forces grow so extreme that the usual rules governing space and time break down entirely. In these conditions, the familiar ideas of here and now no longer hold. A singularity is not merely a location within the universe. It exists outside the conventional fabric of reality. It sits at the crossroads of two monumental theories: general relativity, which describes gravity and the behavior of stars, galaxies, and cosmic structures on a vast scale, and quantum mechanics, which governs the probabilistic world of atoms and subatomic particles. The challenge is that no unified theory, sometimes called quantum gravity, yet exists to merge these two frameworks seamlessly, leaving the true nature of singularities tantalizingly out of reach. Physicists have long attempted to define singularities within the context of general relativity, the most complete theory of gravity currently available. Some describe them as points where the curvature of space becomes infinite, where the fabric of space bends beyond recognition. Others define them through geodesics, the paths that objects follow naturally through space, which suddenly terminate or become incomplete, as though the universe itself has reached a dead end. According to general relativity, when a massive star collapses beyond a critical threshold known as the Schwarzschild radius, it forms a black hole. Beyond the event horizon, the boundary of no return, lies the singularity, a point where matter compresses to infinite density. In this model, even the universe itself began as a singularity during the Big Bang, a point of unimaginable density and heat at the dawn of time. Yet general relativity falters under such extreme conditions. At these scales, quantum effects dominate. Quantum mechanics dictates that particles cannot be confined to a space smaller than their Compton wavelength, which fundamentally challenges the notion of infinite density. Many areas of physics encounter mathematical singularities, points in equations where values diverge toward infinity or cease to make sense, signaling the limits of current theories. Historical examples include the ultraviolet catastrophe, the renormalization processes needed in quantum field theory, and early instability predictions for hydrogen atoms. In classical theories, a singularity is merely a mathematical oddity where the usual equations fail, while space and time remain otherwise regular. In general relativity, however, the breakdown is far more dramatic. Space and time themselves become undefined, rendering conventional descriptions of location and time irrelevant. Some modern theories even suggest that singularities might not exist at all. Loop quantum gravity, which attempts to unite quantum mechanics with gravity, envisions space as composed of tiny loops, introducing a smallest possible size for regions of space. In this framework, gravity ceases to intensify beyond this minimal scale, preventing true singularities from forming. Other approaches propose that the inherent spread of quantum waves counteracts extreme gravitational collapse, softening or eliminating the infinite curvature predicted by classical general relativity. Inspired by this, some scientists have reconsidered geometry itself, redefining points as extended regions rather than zero-dimensional objects. Mathematician Felix Klein, whose work fused geometry with arithmetic, proposed that uncertainty is intrinsic to all measurements, a principle that may influence the structure of space at its most fundamental level. Singularities themselves are not uniform. They can adopt various forms depending on the conditions and the theory in question. Some are conical, resembling the tip of an ice cream cone where the smooth fabric of space abruptly ends. Others may curve in more complex ways, and in rare theories, some might even exist outside the concealment of an event horizon, creating so-called naked singularities visible to the universe. Conical singularities offer a striking visual. Imagine a flat, smooth sheet of paper that suddenly spikes into a sharp point. At this apex, the usual tools of mathematics fail as quantities that are normally stable either diverge toward infinity or remain undefined. Yet this breakdown is local. Outside the tip, space can behave normally, and measurements remain well-defined. Cosmic strings, hypothetical thin filaments of energy stretching across the cosmos, provide an example of such singularities. In a simple, non-spinning Schwarzschild black hole, the singularity is a single point. For spinning Kerr black holes, the singularity forms a ring, a loop in space-time, that some theorists have suggested could serve as the mouth of a wormhole connecting distant regions of the cosmos. More broadly, physicists determine the presence of a singularity by examining geodesic incompleteness. Paths that objects would naturally follow suddenly end, as if the universe itself ceases to continue. For example, an object falling into a non-rotating black hole reaches the singularity in finite time and cannot proceed further. The classical Big Bang model similarly implies a singularity at the inception of the universe, a moment when all matter, energy, and space-time were compressed into infinite density, temperature, and curvature. Until the early 1990s, the prevailing belief was that all singularities were safely cloaked behind event horizons, shielded from the universe in accordance with the cosmic censorship hypothesis. This notion was challenged in 1991 when physicists Stuart Shapiro and Saul Tucholsky ran simulations of a rotating disk of dust. Their results hinted at the possibility of singularities forming without surrounding event horizons, naked and observable to the universe. The existence of such objects remains hypothetical, their appearance and impact on cosmic dynamics still a profound mystery. The question of whether black holes truly have centers, or if they harbor structures even stranger than singularities, remains one of the most captivating frontiers in astrophysics, inviting us to reconsider our understanding of space, time, and the ultimate architecture of reality itself. However, some scientists propose that even in extreme cases, light approaching the singularity of a black hole would behave in a way that makes the object appear as a black hole, regardless. The paths light follows, known as geodesics, would abruptly end at the singularity, effectively cloaking it. Fascinatingly, in the Kerr solution, a model describing spinning black holes, event horizons can vanish if the black hole rotates rapidly enough. In such scenarios, the singularity itself could become exposed to the outside universe, creating a rare and extraordinary possibility known as a naked singularity. Before Stephen Hawking introduced the groundbreaking concept of Hawking radiation, the question of whether black holes could possess entropy, a measure of disorder and thermal content, was largely ignored. Hawking demonstrated that black holes do indeed emit energy through a slow and enigmatic process, almost like a faintly glowing celestial object. This insight resolved a profound problem in physics, confirming that black holes do not violate the second law of thermodynamics, which dictates that the universe's total entropy must never decrease. Since entropy is intimately tied to temperature, this implied that black holes themselves must have a temperature. As a result, black holes gradually lose energy by radiating, slowly shrinking over immense spans of time. Intriguingly, a black hole's temperature is inversely proportional to its mass. The larger the black hole, the colder it is. All black holes discovered so far are so massive that their temperatures remain far below the cosmic background temperature, meaning they are currently absorbing energy rather than losing it. Only when the cosmic background cools significantly below the black hole's own temperature will these titanic objects begin to shrink. This threshold will be reached when the universe's redshift exceeds 1 million, a monumental shift from the current redshift of approximately 1,000, which occurred when the cosmic microwave background first emerged. The holographic principle presents a staggering and almost poetic concept originating from string theory and quantum gravity. It suggests that everything within a three-dimensional space, even the entirety of a room or the universe itself, can be fully described by information stored on a surrounding two-dimensional surface. Much like a hologram, where a flat surface produces a three-dimensional illusion, the universe we perceive could be a three-dimensional projection of data encoded on a distant two-dimensional boundary, such as the edge of space or the horizon of a black hole. This revolutionary idea was initially introduced by Gerard Hooft and later expanded and clarified by Leonard Susskind, who applied insights from string theory to explain it more rigorously. Susskind drew inspiration from 't Hooft and Charles Thorne, another physicist exploring similar concepts, describing our three-dimensional world of stars, planets, mountains, and human structures as a holographic projection of information imprinted on a distant two-dimensional surface. In 1978, Charles Thorne observed a remarkable feature within string theory. It permitted gravity to be described using fewer dimensions. Raphael Bousso later noted that Thorne's observation was a precursor to modern holographic principles. One well-known manifestation of this idea is the ADS-CFT correspondence, a profound theoretical framework linking two distinct physics theories, demonstrating how holography could operate in practice. The holographic principle itself draws deep inspiration from black hole physics, specifically from the Bekenstein bound. This bound asserts that the amount of entropy, or disorder, in a region of space scales not with its volume, which grows cubically with radius, but with the area of its boundary, which grows quadratically. This insight suggests that the surface, rather than the interior, might encode all information about an object. For black holes, this implies that everything falling in is recorded on the event horizon, the surface marking the point of no return. The holographic principle also provides a potential solution to the black hole information paradox, which questions whether information is lost when something falls into a black hole. According to holography, the information is not lost but preserved on the horizon. However, some solutions to Einstein's equations, such as Wheeler's bags of gold, hint at regions storing more entropy than the surface area alone would allow, challenging the principle. These exceptions suggest that a full understanding will require a theory uniting holography with quantum gravity. Expanding the lens even further, most people imagine the universe as composed solely of matter and energy, the tangible things we can observe and measure. Yet in a 2003 Scientific American article, physicist Jacob Bekenstein explored a bolder idea inspired by John Archibald Wheeler, proposing that the universe may fundamentally be made of information, with matter and energy emerging as secondary manifestations. Bekenstein invoked poet William Blake, asking if one could perceive the world in a grain of sand, hinting that reality in its entirety could be encoded in a simple, compact form akin to a hologram. In his article, A Tale of Two Entropies, Bekenstein examined the profound connections between information theory, which governs data storage and communication, and classical physics, the framework describing motion and forces. This connection traces back to Claude Shannon's 1948 work, which introduced Shannon entropy, a measure of information content. Shannon's ideas now underpin modern communication technologies, from cell phones and modems to hard drives and DVDs, forming the backbone of today's data-driven world. Thus, the holographic principle is far more than a concept limited to black holes or distant galaxies. It weaves together the deepest laws of physics with the fabric of information, potentially reshaping our understanding of reality itself. At the intersection of this exploration lies thermodynamics, the study of heat and energy flow, grounding these abstract theories in the tangible dynamics of our universe. One of the most profound and transformative concepts in thermodynamics is entropy. Often, people describe entropy simply as a measure of disorder, the level of chaos or messiness within a system. It reflects how intermixed and jumbled the particles of matter and energy are at a microscopic scale. Yet in 1877, an Austrian physicist named Ludwig Boltzmann took this idea far beyond vague intuition and provided a precise, groundbreaking formulation. Boltzmann proposed that entropy is a measure of the number of microscopic arrangements, configurations of tiny particles like atoms and molecules, that yield the same overall appearance of a system from the outside. Consider, for instance, the air in a room. Each molecule of gas can occupy an almost infinite number of positions and follow countless paths, yet to the human eye, the room seems uniform and unchanging. Boltzmann's insight was that every single one of these invisible, microscopic arrangements contributes to the total entropy of the system. He even formulated a mathematical expression to quantify this, using logarithms to manage the unimaginably vast numbers involved, since the possible configurations of molecules are astronomically large. Decades later, a man named Claude Shannon, working in an entirely different domain, information theory, made an astonishing parallel discovery. While developing methods to measure the amount of information in messages transmitted by telegraph, Shannon devised a formula almost identical to Boltzmann's. Shannon's contribution laid the foundation for the digital age, underpinning modern computing and digital communications. In August of 2003, Jacob Bekenstein, writing for Scientific American in an article titled "Information in the Holographic Universe," highlighted an extraordinary connection. Although Boltzmann studied the microscopic behavior of matter and energy, and Shannon studied messages and data, both were fundamentally quantifying the same concept: the number of ways a system could be arranged. The difference lay in units. Thermodynamic entropy is expressed in terms of energy and temperature, while Shannon's informational entropy is measured in bits, the basic units of digital information. And yet, the story grows even stranger and more captivating. In physics, there exists a bold, revolutionary hypothesis known as the holographic principle. According to this principle, all the matter, energy, and space in the universe may behave like a hologram. Everything we perceive in 3 dimensions might actually be a projection originating from a 2-dimensional surface, potentially the boundary of the universe itself. Within this framework, entropy defies intuitive expectations. It is not proportional to the volume of a region, but rather to its surface area, as if all the information about the contents is encoded on the outer boundary. This idea is deeply linked to a concept called the ADS-CFT correspondence, also known as Maldacena duality, named after physicist Juan Maldacena, who first proposed it in 1997. This mind-bending duality bridges 2 radically different theoretical frameworks. On one side are models of curved spacetime known as anti-de Sitter spaces, central to string theory and quantum gravity. On the other side are conformal field theories, highly sophisticated mathematical structures used to describe particles and forces in quantum physics. The beauty of this duality lies in its practical power. It allows physicists to study extremely complex quantum systems by translating them into problems in gravity, where the mathematics is often far more tractable. This approach has illuminated mysteries across nuclear physics, condensed matter physics, and even the elusive interiors of black holes. Following Maldacena's pioneering work, physicists such as Stephen Gubser, Igor Klebanov, Alexander Polyakov, and Edward Witten expanded and refined the theory. By 2015, Maldacena's original paper had been cited over 10,000 times, solidifying its status as one of the most influential works in modern theoretical physics. Entropy also provides profound insights into black holes, some of the most enigmatic objects in the universe. High-entropy systems, like hot gases, exhibit extreme randomness and microscopic unpredictability. In contrast, perfectly ordered structures, such as precise electric or magnetic fields, have 0 entropy because they contain no intrinsic disorder. For years, scientists assumed that black holes, perfect solutions to Einstein's equations, were similarly devoid of entropy. They appeared flawless, immutable, and entirely ordered. Yet, Jacob Bekenstein recognized a deep inconsistency. The second law of thermodynamics, one of the foundational principles of science, dictates that the total entropy of the universe must never decrease and should generally increase over time. Black holes, with their seemingly perfect order, presented a direct challenge to this law. However, if you hurl something chaotic and energetic, like a swirling mass of hot gas, into a black hole, the universe appears to perform a cosmic sleight of hand. This gas, filled with disorder and random motion, what physicists call entropy, seems to vanish as soon as it crosses the black hole's invisible boundary, the event horizon. Once inside, all traces of the gas's previous state, its temperature, motion, and structure, are inaccessible to the outside universe. The black hole swallows it, smooths out the chaos, and resumes an eerie calm, almost as if the rules governing entropy had been broken. This apparent violation puzzled scientists for decades. To unravel this mystery, Jacob Bekenstein proposed a revolutionary idea. What if black holes themselves possess entropy? What if, when a black hole consumes matter, its own entropy increases by an amount exceeding what it absorbed? In this way, the second law of thermodynamics, the law stating that the total disorder in a closed system never decreases, remains intact. Imagine observing a specific region of space. According to Bekenstein, if that space were entirely filled by a black hole, that black hole would represent the maximum possible entropy for the region. The reasoning is subtle but profound. If another system within the same volume could contain even more entropy, adding matter to it would eventually transform it into a black hole. But then the resulting black hole would have less entropy than the original system, violating the second law. Therefore, a black hole is the ultimate container of entropy for its size, the reigning champion of disorder. Bekenstein worked through the numbers. He considered a spherical volume with radius r filled with a relativistic gas, a gas moving at near light speeds. The entropy of this gas increases as energy increases. But there's a cosmic catch. Add too much energy and gravity takes over, collapsing the gas into a black hole. This sets a natural limit, a cosmic cap on how much entropy any region of space can hold. From this insight, Bekenstein concluded that maximum entropy does not scale with volume, as one might naively expect, but with the surface area enclosing the space. Specifically, a black hole's entropy is proportional to the area of its event horizon, the boundary marking the point of no return. The story becomes even stranger when time itself enters the equation. Gravitational time dilation, a consequence of Einstein's general relativity, causes time to appear to freeze at the event horizon for an outside observer. Nothing can travel faster than light, and from afar, objects never seem to actually cross the horizon. Instead, all information about the swallowed matter, the quantum properties, the hidden details, becomes imprinted on the event horizon, stored like a cosmic ledger on its surface. Meanwhile, Stephen Hawking had already shown that the surface area of black holes never decreases. The event horizon is shaped by special light paths called light-like geodesics, the rays of light that cling to the brink of escape. When nearby geodesics converge, they fall inside the black hole, leaving only those that spread outward to define the horizon. Consequently, the horizon's area can only grow over time. Hawking called this principle the second law of black hole thermodynamics, echoing the familiar law from classical physics. Initially, Hawking doubted black holes could behave like ordinary thermal objects. He assumed they had zero temperature, emitting no radiation and therefore incapable of thermal equilibrium. But his calculations led to a stunning revelation. Black holes do radiate energy, a phenomenon now known as Hawking radiation. In thermodynamics, adding energy to a system increases its entropy in proportion to the energy added divided by temperature. If black holes possess entropy, they must also have a temperature, enabling energy exchange with their surroundings. They not only absorb photons and particles of light, they must emit them to maintain equilibrium with the surrounding cosmic environment. This discovery turned conventional expectations upside down. Systems that are time-independent, unchanging in time, typically cannot radiate because they conserve energy perfectly. Hawking expected the same for black holes, yet precise calculations showed otherwise. Black holes emit radiation in just the right way to reach thermal balance with their surroundings. From this, Hawking derived a precise measure of a black hole's entropy. It is 1/4 of the event horizon's area, expressed in natural units known as Planck units. Entropy in physics represents the number of microscopic arrangements of a system that produce the same macroscopic appearance. Bekenstein and Hawking revealed something extraordinary. A black hole's hidden internal arrangements, the microstates that account for its entropy, are not linked to its volume, but solely to the area of its event horizon. This counterintuitive discovery remains one of the most profound puzzles in modern physics. Later, Raphael Bousso expanded on Bekenstein's insights, generalizing the concept through surfaces called null sheets, extending the principle to a broader array of scenarios. Hawking's earlier revelation that black holes, once thought to trap everything permanently, emit a faint glow, added another layer of mystery. This radiation carries no specific information of the matter that fell in. The black hole seems to forget its past entirely. Like a cosmic vacuum cleaner, it devours matter and light. Yet, the energy that escapes offers no clues to the contents consumed. The universe, in the presence of a black hole, rewrites the rules of information, entropy, and the very fabric of space and time. The light that manages to escape a black hole appears to linger right at the edge, hovering along the boundary known as the event horizon for an astonishingly long period. Meanwhile, matter plunging into the black hole doesn't even approach that edge until much later, and the interaction between the falling and outgoing energy occurs only for a fleeting instant. That brief encounter is far too short to transmit all the intricate information carried by the infalling matter. It seems almost impossible that the escaping light could somehow encode the details of what went in through such a minor interaction. Stephen Hawking proposed that this implied a profound consequence. When a black hole absorbs pure particles of light, photons, which are elegantly described in quantum mechanics by a wave function, it emits entirely new photons that are fundamentally different. These newly emitted photons emerge not as a neat, predictable wave, but as a chaotic haze, a fog of possibilities described not by a wave function, but by a more disorderly structure known as a density matrix. If this is indeed the case, it presents a severe challenge to the foundations of physics. Quantum mechanics dictates that a pure state, a pristine wave, should never spontaneously transform into a mixed state, a random cloud, without external interference. If black holes can do this, it suggests that quantum mechanics may be incomplete or flawed in some essential way. This enigmatic puzzle became famously known as the black hole information paradox, leaving physicists around the world puzzled and intrigued. Among them was Gerard Hooft, a visionary physicist who took a closer look at Hawking radiation. He proposed that the radiation escaping a black hole might actually carry subtle imprints of the matter falling in. As particles spiral toward the black hole, their gravity can slightly warp the event horizon, creating minute distortions that influence the characteristics of the particles emitted. According to T. Hooft, each particle falling into a black hole generates a tiny bump, a localized protrusion on the smooth horizon, much like a tent pole rising from a flat surface. Though these bumps are incredibly small, they encode crucial information, acting as fingerprints of the particle's mass and position. In simple spherical black holes without electric charge, these distortions resemble the behavior of particles in string theory, where fundamental particles are envisioned as tiny vibrating strings. This insight led Hooft to propose that black holes could be described using the intricate mathematics string theory, with all the information of infalling particles stored in the horizon's minute ripples. Much like a hologram encodes a three-dimensional image on a two-dimensional surface. Leonard Susskind expanded on this idea through the holographic principle, which posits that all information within a volume of space can be represented on its boundary, essentially turning the universe itself into a cosmic hologram. Susskind suggested that the black hole's fluctuating surface could fully encode both what falls in and what comes out. He observed that the behavior of strings in string theory aligns perfectly with this holographic vision. Small, simple strings carry no entropy, meaning no information is lost, while larger, more complex strings behave analogously to ordinary black holes. This indicated that black holes and strings might be dual aspects of the same underlying reality. Thanks to these breakthroughs, the black hole information paradox began to take shape as a solvable problem. If quantum gravity, the theoretical framework uniting quantum mechanics and gravity, is governed by string theory, then perhaps no information is ever truly lost. Everything falling into a black hole could be recorded in the infinitesimal vibrations of its surface. In this perspective, space and time themselves are emergent phenomena arising from the complex dynamics of the black hole horizon. In 1995, Susskind, along with colleagues Tom Banks, Willy Fischler, and Stephen Schenker, proposed a revolutionary approach to M-theory, a master theory encompassing all string theories. They introduced a holographic description using D0 branes, tiny supercharged black holes within type 2A string theory. Interestingly, earlier work by Bernard DeWitt, Jens Hoppe, and Hermann Nicolai had already hinted at similar ideas, showing that certain 11-dimensional objects in supergravity could be described using matrices, grids of numbers capable of encoding complex systems. Later, these matrices were understood to also model the behavior of small black holes under specific conditions. Through the holographic principle, Suskind's team realized that the motion and interaction of these small black holes could encode the entirety of M-theory, providing a non-perturbative formulation capable of describing both simple and highly complex scenarios. In 1997, Juan Maldacena advanced this concept further, demonstrating a concrete example of a holographic duality for a four-dimensional object known as the Type 2b brane. This breakthrough solved a long-standing challenge: how to represent gauge theories, which describe forces like electromagnetism and the strong nuclear force in terms of string theory. Maldacena's work revealed profound connections between string theory and certain supersymmetric quantum field theories. A crucial concept in this discussion is information entropy, which quantifies the uncertainty or randomness in a system. The more possible microscopic configurations a system has, the greater its informational content. Physicists calculate this by taking the logarithm of the inverse probability of a system occupying a particular state. The less likely the state, the more information it conveys. Averaging this over all possible states produces the system's entropy, aligning with Gibbs' classical notion of entropy developed over a century ago. Applied to the universe, this concept yields a striking insight. Any given volume of space with a finite amount of energy can hold only a limited amount of information, a limit known as the Bekenstein bound. Exceeding this bound causes the space to collapse into a black hole, establishing an ultimate limit on the information that matter can contain. This principle implies a fundamental granularity in the fabric of matter. Particles cannot be subdivided endlessly. There must exist a final, irreducible level akin to the ultimate Lego bricks of the cosmos. If subparticles could continue infinitely, their degrees of freedom would also be infinite, violating the entropy limit. The holographic principle, therefore, imposes a profound restriction on the depth to which matter can be divided. The most precise formulation of this principle is the ADS-CFT correspondence, introduced by Maldacena. It establishes a detailed duality between two seemingly distinct frameworks, a theory in curved space called anti-de Sitter space and a conformal field theory residing on its boundary. This correspondence provides a concrete bridge between gravity in higher dimensions and quantum field theories, offering a revolutionary lens through which to understand the universe at its most fundamental level. But even earlier, back in the year 1986, physicists David Brown and Mark Hino stumbled upon a remarkable discovery that would quietly ripple through the foundations of theoretical physics. They showed that the symmetry inherent in three-dimensional gravity, consisting of two spatial dimensions and one of time, naturally leads to a profound mathematical structure now known as the Vazzaro algebra. This abstract framework would go on to play a pivotal role in understanding two-dimensional conformal field theories, connecting deep mathematical insights with the fabric of the cosmos. Fuzzballs emerged from an equally imaginative, almost poetic branch of physics called superstring theory, a framework designed to reconcile the dizzying contradictions between the infinitely small world of quantum mechanics and the vast, curved arena of Einstein's general relativity. Black holes, traditionally, are enigmatic voids where gravity is so intense that nothing, not even light, can escape, and the central singularity is considered an infinitely dense, unknowable point. Fuzzballs, however, offer a radical reimagining. Rather than harboring a single infinitely compressed point, black holes could instead be colossal, tangled spheres composed entirely of minuscule, vibrating strings. In string theory, the very fabric of reality is woven from these fundamental loops of energy. Far smaller than atoms, strings vibrate in complex patterns, with each vibration determining the type of particle or energy it manifests. These oscillations do not confine themselves to the three visible dimensions. They ripple through additional hidden dimensions, compacted so tightly that they escape direct detection. The fuzzball hypothesis posits that the interior of a black hole, up to the so-called event horizon, the boundary beyond which escape is impossible, is filled not with a void, but with a dynamic tangle of these strings, giving the object a fuzzy, textured appearance. This reinterpretation resolves two long-standing problems that have haunted physicists. First, it eliminates the singularity, the theoretical point of infinite density where conventional physics fails. Many scientists now suspect singularities are not actual entities, but rather signposts indicating the incompleteness of our theories. Fuzzballs replace the incomprehensible singularity with a tangible, dense, vibrating mass of strings. Second, fuzzballs confront the black hole information paradox. Classical theory implies that information about matter falling into a black hole is irretrievably lost, violating the principles of quantum mechanics. Fuzzballs preserve this information encoded in the structure of the string network that constitutes their surface, thus safeguarding the universe's ledger of quantum data. Yet, this theory remains speculative, unconfirmed by direct observation. Its foundation lies entirely in rigorous mathematics and intricate calculations. Nevertheless, future experiments, especially those involving gravitational wave detection, may reveal indirect evidence by analyzing the ripples generated in spacetime during black hole collisions. A central figure in developing the fuzzball concept is Samir D. Mathur of Ohio State University, who between 2001 and 2012 published a series of papers that re-envisioned black holes as full spherical structures of strings. Collaborating initially with Oleg Lunin, Mathur constructed a coherent vision in which black holes are not empty voids with a single point of doom, but intricate, string-filled entities. In all formulations of string theory, these fundamental strings underpin not just particles like electrons or quarks, but also force carriers such as photons for light and gluons for the strong nuclear force. The fuzzball concept arises from a particular model called Type 2b string theory, in which strings may be open-ended or closed loops, and the universe comprises 9 spatial dimensions plus 1 of time. 6 of these spatial dimensions are theorized to be curled up beyond perception, influencing the behavior of strings in subtle ways. Small fuzzballs resemble ultra-dense neutron stars, one of the universe's densest objects, though taken to extremes unimaginable in conventional astrophysics. Within these stars, neutrons fragment into quarks and then into strings, signifying that a fuzzball represents the ultimate endpoint of matter, compressed beyond ordinary limits. Mathematical analyses indicate that a fuzzball surface coincides with the event horizon predicted by classical theory. For instance, a black hole with a mass approximately 6.8 times that of our Sun would have a Schwarzschild radius around 20 kilometers, or roughly 12.5 miles. The fuzzball, rather than forming a rigid boundary, presents a soft, mist-like surface, teeming with activity at scales far smaller than atoms. In the classic model, any matter crossing the event horizon is inexorably drawn toward the singularity, crushed by the unstoppable curvature of spacetime. Fuzzballs, in contrast, absorb matter into the dense network of strings, ensuring that information is never truly lost. Observed from a distance, a fuzzball behaves identically to a traditional black hole, obeying Einstein's equations of gravity. The divergence arises only when probing the quantum regime, where the minutiae of particle interactions reveal the tangled interior. Proponents of the theory argue that this quantum description offers the truest representation of black holes, supplanting the notion of an infinitely dense point with a physically comprehensible structure. A surprising property of fuzzballs is that their density decreases as mass increases, a phenomenon known as fractional tension. Incoming strings merge with existing ones, forming increasingly complex networks that stretch farther without increasing tension proportionally. This means larger fuzzballs expand in size while their overall density diminishes. Mathematical formulas derived by Mathur and Lunin align perfectly with Schwarzschild's calculations from 87 years earlier, confirming that the event horizon's radius grows with mass, while density falls according to the cube of the radius. For example, a fuzzball weighing 6.8 solar masses would have an average density around 4 times 10 to the power of 17 kilograms per cubic meter. A mere droplet of this material, the size of a raindrop, would weigh 20 million metric tons, comparable to a granite sphere over 200 meters in diameter, but still far from infinite density. Even the densest fuzzballs remain orders of magnitude below Planck density, the theoretical upper limit of matter compression, estimated at over 5 times 10 to the power of 96 kilograms per cubic meter. Extremely massive fuzzballs, such as those exceeding 7 solar masses, could be less dense than neutron stars, and supermassive examples, like the one at the center of the Milky Way, might have average densities only modestly greater than everyday substances. Fuzzballs and classical black holes originate primarily from violent cosmic events, supernovas, kilonovas, and hypernovas, where stellar material is ejected and compressed. Yet they can also form quietly, as a neutron star slowly accrues mass beyond the Tolman-Oppenheimer-Volkoff limit, estimated between 2.2 and 2.9 solar masses. At this threshold, the star collapses under its own gravity. Traditional physics predicts a singularity and event horizon, while fuzzball theory envisions a seamless transition, with neutrons decomposing into strings and creating a quantum black hole. Classical black holes have long challenged scientists with the black hole information paradox, a puzzle that fuzzballs may finally resolve, offering a vision of the universe where gravity, quantum mechanics, and cosmic structure coexist in a coherent, string-filled tapestry. But according to a newer concept known as the fuzzball theory, what has long been considered a paradox might not be one at all. The story of this cosmic mystery begins in the early 1970s. In the year 1972, a physicist named Jacob Bekenstein proposed that something profoundly unusual could be occurring with information trapped inside black holes. His idea sparked curiosity, but it was the renowned scientist Stephen Hawking who brought the issue into the global spotlight, captivating the imaginations of physicists everywhere. At the heart of the paradox lies a collision between two pillars of modern science: quantum mechanics and general relativity. Quantum mechanics, the discipline that governs the behavior of the universe's tiniest constituents, particles smaller than atoms, asserts that information about these particles can never simply vanish. On the other hand, general relativity, the framework that explains gravity and the behavior of massive cosmic objects like stars and galaxies, implies that if a black hole contains a singularity, a point of infinite density and infinitesimal size, then any information swallowed by the black hole is lost forever. This creates a fundamental contradiction. Quantum mechanics and general relativity are like two brilliant thinkers whose perspectives refuse to converge. One explains the universe in terms of its smallest building blocks, the other in terms of colossal celestial objects. For decades, scientists have struggled to reconcile these two conflicting views, searching for a framework that unites them without contradiction. This is where fuzzball theory enters the narrative. Rooted in the intricate mathematics of type 2b superstring theory, fuzzball theory belongs to a broader paradigm known as supergravity, which seeks to describe gravitational phenomena using the principles of quantum physics. Imagine a black hole that primarily consumes ordinary matter, protons, neutrons, and electrons from a neighboring star. Compare it to a black hole that feeds solely on light, swallowing photons from distant stars or the cosmic microwave background. According to quantum mechanics, these two black holes should have fundamentally different internal structures because the matter they consume is distinct. Physics dictates that the state of a system at one moment should determine its state at all other times. General relativity, however, tells a different story. Once anything crosses the event horizon, the boundary of a black hole, all distinctions vanish. Both black holes, regardless of their dietary differences, would appear as nothing more than singularities, devoid of size, structure, or any ability to preserve quantum information. Even if information were somehow preserved inside, it could never escape, because the gravitational pull near the center of a black hole is so intense that not even light can break free. This concept is captured by the no-hair theorem, which asserts that black holes are externally simple. Observers can determine only a black hole's mass, spin, angular momentum, and electric charge. All other details, including the history of what fell in, remain hidden forever. Adding to the enigma, Stephen Hawking demonstrated that black holes emit minuscule amounts of radiation due to quantum effects, now known as Hawking radiation. The paradox deepens because this faint glow reveals nothing about the black hole's internal composition, except for its mass. Black holes, in effect, glow without ever disclosing their deepest secrets. Fuzzball theory transforms this picture. According to physicists Samir Math and Oleg Lunin, black holes are not empty, featureless singularities. Instead, they are intricate tangles of vibrating strings, forming a structure reminiscent of a fuzzy ball. Each string carries quantum information. When matter falls onto the fuzzball, it integrates into this tangled structure, and the information it contains becomes a permanent component of the fuzzball itself. Crucially, this information is not eternally trapped. Some of it can tunnel through the fuzzy surface and leave an imprint on the Hawking radiation, which gradually carries tiny fragments of this information back into the universe. The fuzzball, in essence, whispers secrets back into the cosmos, particle by particle, bit by bit. This mechanism offers a potential resolution to the black hole information paradox, allowing quantum mechanics and general relativity to coexist in harmony. Yet, fuzzball theory remains entirely theoretical. There is currently no experimental evidence to confirm it. Nevertheless, it represents one of the most promising approaches to understanding how gravity operates within the quantum realm, a quest known as developing a theory of quantum gravity. The theory emerges from one of 5 versions of superstring theory, all of which are thought to be components of an even more comprehensive framework called M-theory. None of these versions have been experimentally validated, but they all provide models that incorporate quantum gravity. For a theory to enter the canon of established science, it must make predictions that are testable and verifiable. Superstring theory, for instance, predicts the existence of elusive particles called superpartners, which have yet to be discovered, though the search continues. Direct confirmation of fuzzball theory through Hawking radiation remains impossible for now, because the radiation is far too faint for current technology to detect, leaving this tantalizing glimpse into the universe's hidden structures still beyond our reach. However, there is a glimmer of hope that some of these ideas might be testable through the study of gravitational waves, those subtle ripples in the very fabric of space caused by the titanic collisions of massive objects like black holes. Yet the path is riddled with complications. Take fuzzball theory, for instance, which is rooted in the complex idea of supersymmetry. Supersymmetry suggests that every particle in the universe has a hidden partner. For every familiar particle, such as a photon, the massless particle of light, there exists a predicted counterpart called a photino, a particle that is heavier and spins in a different, almost ghostly way. Electrons, the well-known particles with mass and half-spin, are predicted to have ethereal partners that are massless and spinless, like intangible shadows dancing alongside their corporeal twins. These superpartners are strange not only in their ghost-like qualities, but also in how differently they behave compared to ordinary particles. While standard particles like protons and electrons cannot occupy the same space due to the principles of quantum mechanics, some of their superpartners could potentially overlap effortlessly, behaving more like bosons, particles that are far less constrained. If these elusive superpartners do exist, they could provide crucial clues about why the universe is structured the way it is. Yet, without direct detection, they remain tantalizingly hypothetical. The discovery of these superpartners would be revolutionary. Not only would it lend strong support to superstring theory, but it could also solve some of the most perplexing mysteries in modern physics. For instance, they might explain the composition of dark matter, the invisible scaffolding of the cosmos, and clarify anomalies such as the slight deviation in the magnetic behavior of a particle called the muon. The muon's magnetic moment, theoretically expected to equal exactly 2, is in reality slightly higher at approximately 2.00233184, a tiny discrepancy hinting at the influence of unknown forces or hidden particles. This has driven particle physicists into decades of diligent searches for superpartners, though success has been elusive. Dark matter itself presents a colossal puzzle. Its existence is inferred from its gravitational effects on galaxies and the universe's expansion, yet its precise composition remains shrouded in mystery. If it is made of tiny particles, their detection is extremely challenging. Since 1986, scientists have pursued them with every method imaginable, yet they have remained undetected. According to supersymmetry, the lightest of these superparticles would be stable electrically neutral and interact very weakly with ordinary matter, making them nearly invisible to even the most sensitive instruments. Particle colliders, vast machines designed to smash particles together at incredible speeds, have eliminated some potential mass ranges, but the search is far from over. Fuzzball theory offers another profound twist. It attempts to reconcile 2 of the most fundamental yet seemingly incompatible frameworks of physics, general relativity and quantum mechanics. In this theory, the information that falls into a black hole is not obliterated, as Stephen Hawking once suggested, but rather preserved in a fuzzy, cloud-like structure called a fuzzball. The tiny fragments of radiation, Hawking radiation, carry this information in the subtlest way imaginable, emanating from a chaotic quantum foam just above the fuzzball's surface. Detecting this radiation is nearly impossible because the energy levels involved are unimaginably low. A black hole with roughly 5 times the mass of our sun would require 10 to the power of 59 times the current age of the universe to evaporate completely. For supermassive black holes weighing billions of times more, the timeline stretches to an astronomical 10 to the power of 90 times the age of the universe. Hawking also revealed that a black hole's radiation energy depends on its size. Smaller black holes emit more energetic radiation, yet even the tiniest known black holes, with masses around 3 times that of the sun, release photons with energies so faint they correspond to a temperature just 23 billionths of a Kelvin above absolute zero. The total power released would be approximately 1.2 times 10 to the negative 29 watts, equivalent to an almost inconceivable fraction of a milliwatt. Put into perspective, this is like comparing one tiny drop of water to all the oceans on Earth. The challenge is compounded by the fact that such radiation arrives in the form of individual photons. So, a small black hole might emit merely 10 photons per second. Even if such a black hole were a mere 100 light-years away, the odds of detecting a photon with a telescope at the precise moment a human observes it are vanishingly small. For supermassive black holes at the hearts of galaxies, the problem becomes even more extreme. For example, the supermassive black hole M87 may release only 13 photons every century, and the radiation's wavelength is so long that any detector capable of catching it would need to span beyond the entire solar system. Despite these staggering challenges, fuzzball theory might still be testable through gravitational waves. These ripples in space-time, caused by colossal collisions of massive objects, have transformed our ability to observe the universe. Instruments like LIGO, the Laser Interferometer Gravitational Wave Observatory, have revolutionized astronomy. The first detection in 2015, the event named GW150914, caused by 2 black holes merging, aligned perfectly with predictions from conventional black hole physics. Yet in 2021, Italian scientists running detailed computer simulations suggested that fuzzballs might leave subtle signatures in gravitational waves. These signs could emerge during the final ring-down phase after black holes merge, analogous to the fading resonance of a bell. Fuzzballs would cause these vibrations to decay more slowly and produce echoes of earlier oscillations, phenomena absent in ordinary black holes. Another Italian team had earlier proposed that future observatories like LISA, the Laser Interferometer Space Antenna, could detect these effects even more effectively. LISA is designed to capture gravitational waves from massive black hole mergers at lower frequencies than current detectors, potentially improving our ability to test fuzzball theory by orders of magnitude. Primordial black holes, or PBHs, add yet another layer to this cosmic mystery. Hypothetical remnants from the universe's earliest moments, formed long before the first stars ignited, these black holes defy the usual rules of black hole physics observed today, offering an entirely new frontier of investigation and speculation about the nature of space, time, and matter itself. Normally, black holes are born when a massive star reaches the end of its life, exploding in a cataclysmic supernova and leaving its core to collapse under the immense pull of gravity. But primordial black holes, or PBHs, could have emerged in an entirely different way. During the inflationary era, when the universe was still in its infancy and dominated by intense radiation, tiny yet unimaginably dense pockets of matter may have been squeezed so fiercely that they collapsed under their own weight, forming black holes without the presence of any stars. Since these PBHs would have existed before stars even came into being, they are not confined to the same mass range as regular stellar black holes, which typically weigh a few times more than our sun. This opens up the possibility that PBHs could exist in an astonishing variety of sizes, from minuscule to immense. The concept of primordial black holes was first proposed in 1966 by the Soviet scientists Yakov Zeldovich and Igor Novikov. Just a few years later, in 1971, the legendary physicist Stephen Hawking conducted the first thorough investigation of this idea. Even today, however, these black holes remain hypothetical. No direct evidence has yet confirmed their existence. In September 2022, a team of scientists revisited the PBH hypothesis to shed light on a puzzling discovery made by the James Webb Space Telescope, which had observed colossal galaxies forming far earlier in cosmic history than previously thought possible. PBHs may have played a crucial role in accelerating the formation of these giant galaxies, acting as seeds around which matter quickly coalesced. For decades, PBHs have also been considered a potential explanation for dark matter, the invisible substance that constitutes the majority of matter in the universe yet emits no light. Some researchers speculate that PBHs could account for nearly all of this elusive dark matter. Support for this idea has been bolstered by data from the LIGO and Virgo gravitational wave detectors and the James Webb Space Telescope. Early models assumed PBHs would all share a uniform mass, known as a monochromatic mass distribution, but observations challenged this notion. LIGO and Virgo revealed that black holes exist across a broad range of masses, and recent James Webb data reinforces the idea that PBHs could vary widely in size, possibly clustering around one solar mass, roughly equal to our sun's weight. Some could be as small as asteroids, compressed into a space the size of a hydrogen atom, hurtling through the cosmos at unimaginable speeds. In fact, one could even be wandering within our own solar system. Most of the time, a PBH passing through a star would glide harmlessly through, like a bullet through mist, though a slow-moving PBH might be captured by a star's gravitational pull. Hawking himself speculated that our sun could harbor such a tiny black hole. Depending on the model, a PBH could originate with a mass as small as 10 to the power of -8 kilograms, sometimes called Planck relics, all the way to thousands of times the mass of the sun. However, PBHs lighter than 100 billion kilograms likely no longer exist, having evaporated over time through a process known as Hawking radiation. Only the heavier primordial black holes would remain in the modern universe. Unlike ordinary stars, planets, or people, PBHs consist of non-baryonic matter, further supporting the idea that they could account for dark matter. Some scientists theorize that these ancient black holes may have served as the seeds for the supermassive black holes at the centers of large galaxies, as well as intermediate black holes in smaller galaxies. PBHs belong to a wider category of objects known as massive compact halo objects, or MACOs. These objects are compelling dark matter candidates because they interact minimally with other matter, remain stable if sufficiently massive, and traverse space at slow velocities. Crucially, they would have formed within the first second after the Big Bang. Yet, the scientific community remains divided. Some argue that observational data impose strict limits on PBH abundance, suggesting they could not account for most dark matter. Nevertheless, new research indicates that PBHs may still play a significant role, particularly if they cluster together, with perhaps a 30 solar mass PBH at the heart of each cluster. In March 2016, just a month after the groundbreaking announcement of gravitational wave detection by advanced LIGO and Virgo, 3 research groups proposed a provocative idea. These waves might originate from the merger of 2 PBHs, each about 30 times the mass of the Sun. 2 groups argued that this scenario aligned with the hypothesis that PBHs could comprise all dark matter if clustered in small galactic halos, such as faint dwarf galaxies or globular clusters. The third group disagreed, asserting that the observed merger rate implied PBHs could account for less than 1% of dark matter. These unexpectedly massive black holes reignited interest in PBHs ranging from 1 to 100 solar masses, though debates continue regarding consistency with other observations such as microlensing limits, cosmic microwave background patterns, the scale of small galaxies, and the absence of corresponding X-ray and radio signals near our galactic center. In May 2016, Alexander Kashlinsky proposed a striking idea after analyzing unexplained patterns in gamma-ray and X-ray background radiation. These patterns appeared in regions devoid of visible stars or galaxies. Kashlinsky suggested that they might originate from primordial black holes, which, if sufficiently common and similarly massive, could account for the enigmatic radiation. Then, in August 2019, a study proposed an even more audacious possibility. All of the universe's dark matter could consist of asteroid mass PBHs, tiny yet incredibly dense objects potentially scattered throughout space. Just 1 month later, in September 2019, researchers James Unwin and Jacob Schultz advanced another surprising theory. They posited that a PBH weighing between 5 and 15 times the mass of Earth might be lurking far beyond Neptune in the Kuiper Belt, roughly the size of a tennis ball but extraordinarily dense. Their theory arose from observing distant celestial objects exhibiting unusual motions, hinting at an invisible massive presence, possibly corresponding to the elusive Planet 9, but in fact a primordial black hole. In October 2019, Derek Inman and Yasin Ali Himoud explored whether the formation of cosmic structures could influence measurements of the cosmic microwave background, the relic radiation of the Big Bang. They concluded that these small perturbations would not significantly alter existing CMB data, reinforcing prior constraints on PBH studies and early universe physics. Fast forward to September 2021, when researchers from the Nanograph collaboration reported detecting a low-frequency signal potentially originating from gravitational waves. Some scientists suggested this might be linked to PBHs, offering a tantalizing new indirect detection method. By September 2022, scientists were once again investigating primordial black holes to explain the latest cosmic puzzles, from early galaxy formation to the hidden scaffolding of dark matter, keeping alive the extraordinary possibility that these ancient, invisible objects have quietly shaped the universe since its first moments. The James Webb Space Telescope, hailed as one of the most powerful and sophisticated observatories ever sent into the depths of space, had begun revealing a universe far stranger than scientists had anticipated. It captured images of enormous galaxies. Their vast spiral arms and dense cores formed astonishingly early in cosmic history, appearing billions of years before standard models predicted such structures could exist. These ancient galactic giants posed a profound puzzle. They seemed far too massive and well-developed for the young universe, challenging long-held assumptions about cosmic evolution. Yet, one possibility emerged. Primordial black holes might have acted as cosmic accelerators, seeding these galaxies and allowing them to form far faster and earlier than previously imagined. Then, on November 26, 2023, astronomers made a discovery that electrified the scientific community. For the first time, they reported strong evidence of an overmassive black hole galaxy, or OBG, a rare and extraordinary type of galaxy. Unlike typical galaxies, where black holes form from the collapse of dying stars, OBGs could have formed through direct collapse, a massive cloud of gas condensing immediately into a black hole, bypassing the star stage entirely. This revelation came from observations of a distant early galaxy known as UHZ-1, harboring a blazing quasar at its heart, a celestial beacon powered by a black hole consuming matter with ferocious energy. The discovery relied on combined data from both the Chandra X-ray Observatory and the James Webb Space Telescope, revealing the profound capabilities of multi-wavelength astronomy to unravel cosmic mysteries. In 2024, a comprehensive review led by physicist Bernard Carr and his colleagues delved into the enigmatic origins of primordial black holes. Their research suggested these ancient black holes might have formed during a fleeting phase known as the quantum chromodynamics epoch, occurring in less than 100,000th of a second after the Big Bang. Today, the masses of these primordial black holes appear to follow a distinctive pattern, with several peaks, one notably around one solar mass, strikingly similar to our own sun. But how did these primordial black holes emerge at all? Scientists theorize they could have formed within the universe's first second, during either the elusive inflationary period or the subsequent radiation-dominated era. For a black hole to arise, a region of space must become extraordinarily dense, with gravity collapsing matter inward under its own weight. These regions could stem from minuscule density fluctuations, tiny uneven patches in the distribution of matter in the infant universe. Several mechanisms might have produced these fluctuations. One theory, axion inflation, proposes that a peculiar particle called an axion behaves like a field during inflation, creating ripples of energy across space. These ripples could have planted the seeds of primordial black holes. Another explanation points to reheating, a brief phase following inflation, when the inflaton field, the driver of cosmic inflation, decayed into particles. As these particles collided and sought thermal equilibrium, irregularities could have left pockets of denser matter, later collapsing into black holes. A third possibility involves cosmological phase transitions, moments when the universe underwent radical transformations, analogous to water freezing into ice. These shifts could have produced dense regions or unleashed energy that collapsed under gravity, birthing primordial black holes. Returning to one of the universe's oldest mysteries, dark matter, first proposed in 1933 by Swiss-American astronomer Fritz Zwicky. Observations have long indicated that galaxies and galaxy clusters move as if invisible mass exists far beyond what can be seen. Primordial black holes could help solve this puzzle. If numerous enough, they might constitute all or most of the universe's dark matter. Unlike theoretical candidates like weakly interacting massive particles, primordial black holes can emit gravitational waves, ripples in space-time detectable with modern instruments. They might also explain strange gravitational lensing phenomena, where light from distant stars bends in unusual ways, defying explanation by visible matter alone. Although definitive proof remains elusive, the case for primordial black holes continues to grow. Researchers like Bernard Carr explore their potential to illuminate the earliest moments of the universe. Primordial black holes, or PBHs, are extraordinary, not only because they could have formed mere seconds after the Big Bang, but also because they can exist across an astonishing range of sizes. Some might have been crucial in shaping galaxies, including those that appeared far earlier than standard models allowed. In 1974, Soviet physicist Yakov Zeldovich introduced a major cosmological challenge, the domain wall problem. He proposed that rapid phase transitions in the early universe might have produced invisible energy-laden boundaries called domain walls. If too many formed, they could have disrupted the universe's evolution. Primordial black holes might offer a solution. Their gravity could clump matter, preventing domain walls from forming, or destroy walls that had already emerged, collapsing them into new black holes. In some scenarios, PBHs would exist in such specific mass ranges, from 10 to the power of 12 to 10 to the power of 13 kilograms, that they could account for dark matter while leaving the observable universe intact. Zeldovich also highlighted another conundrum, the cosmological monopole problem. Magnetic monopoles, theoretical particles with only a single magnetic pole, should have been abundant in the early universe, yet remain undetected. Primordial black holes might explain their absence. Monopoles could have been swallowed by black holes or dispersed so widely by gravitational clumping that they became nearly impossible to detect. String theory introduces an even more curious twist. According to general relativity, the smallest primordial black holes should have evaporated over cosmic time due to Hawking radiation. Yet, if an extra hidden spatial dimension exists, as string theory predicts, gravity could act differently at tiny scales. Energy from this hidden dimension might slow PBH evaporation, allowing even minuscule black holes to persist, potentially leaving thousands scattered across the Milky Way. Scientists probe these possibilities with instruments like NASA's Fermi Gamma Ray Space Telescope, launched on June 11, 2008. Observing subtle ripples in gamma-ray bursts could reveal both primordial black holes and the hidden dimensions of space itself. They also study Hawking radiation to estimate PBH abundance and size. While large black holes, like one 3 times the Sun's mass, would take roughly 10 to the power of 69 years to vanish, smaller primordial black holes, perhaps around 10 to the power of 11 kilograms, might have lifespans comparable to the universe itself. If many formed in the Big Bang, some might still be exploding nearby in our galaxy, unleashing bursts of energy comparable to millions of megatons of force. Primordial black holes remain enigmatic, yet their fingerprints may be woven into the fabric of the universe, from the earliest galaxies to the mysterious dark matter, from domain walls to elusive magnetic monopoles, hinting that the universe's first moments were far more dynamic and extraordinary than we ever imagined. NASA's Fermi telescope, which was launched into orbit in June 2008, was built with the goal of catching glimpses of rare cosmic events. Observations from Fermi have now given scientists strong evidence that no more than 1% of dark matter could consist of primordial black holes, or PBHs, with masses up to 10 to the power of 13 kilograms. If these PBHs had been abundant in the early universe, the radiation they emitted would have altered the proportions of light elements like hydrogen and helium created shortly after the Big Bang. Yet, if Hawking radiation does not exist, detecting PBHs becomes an almost impossible task because their tiny size and weak gravitational pull would leave them nearly invisible against the vast backdrop of space. In the earliest moments of the universe, tiny black holes known as primordial black holes may have formed, drawing in nearby matter and releasing bursts of energy into their surroundings. This energy could have influenced a pivotal stage in cosmic history called recombination, when the universe cooled enough for atoms to form. By studying the relic light from the Big Bang, known as the cosmic microwave background, or CMBB, scientists can look for subtle traces of this energy. The CMBB exhibits minute variations in temperature, known as anisotropies, spread across the sky, and these variations can now be measured with astonishing precision. The Planck satellite, which mapped the CMBB in unprecedented detail, indicates that PBHs with masses ranging from 100 to 10,000 times the mass of our Sun likely cannot account for a significant portion of dark matter under the simplest models. However, the debate continues as more complex or realistic models might change these limits. Another tantalizing hypothesis suggests that dark matter, the invisible substance making up most of the universe's matter, could consist of particles called WIMPs, short for weakly interacting massive particles. If PBHs attracted clouds or halos of WIMPs around them, collisions among these particles could produce high-energy gamma rays. Observatories such as the Fermi Gamma Ray Space Telescope are specifically designed to detect this type of light and might eventually catch such signals. In the coming years, several powerful observatories and experiments are set to revolutionize the search for PBHs. The Square Kilometer Array, a massive radio telescope, will investigate how PBHs may have influenced the formation of the first stars and galaxies. If these black holes released energy by accreting matter, they could have altered the timeline of the universe's reionization. Gravitational wave observatories like LIGO and Virgo have already detected merging black holes, and if they observe black holes with masses below 1.4 times that of the Sun, it could suggest a primordial origin rather than formation from dying stars. They can also detect unusual orbital patterns, which might indicate a PBH history. Future detectors will expand this search. LISA, a space-based laser interferometer, and pulsar timing arrays will monitor faint background ripples in space-time caused by PBHs orbiting one another long before they collide. Observations of faint dwarf galaxies and their dense star clusters may reveal PBHs hidden within dark matter-rich environments. Tracking stellar motions in the Milky Way could uncover nearby PBHs influencing the paths of stars. Some researchers even propose listening for unique sound-like signals generated if a tiny black hole passed through Earth, leaving subtle atomic interactions without causing damage. Similarly, starquakes could reveal PBHs passing through stars, producing vibrations detectable by sensitive instruments. Microlensing events, when PBHs bend the light of distant stars or quasars, offer another indirect way to spot them, as does monitoring subtle tugs on planets in our solar system caused by a passing PBH. Although none of these methods are designed solely to detect PBHs, together they form a web of indirect evidence that allows scientists to test theories about these elusive objects. Already LIGO and Virgo have set constraints on PBH populations, showing how gravitational wave detections can hint at exotic origins. Future upgrades, such as Cosmic Explorer and the Einstein Telescope, promise even greater sensitivity, extending the reach of gravitational wave astronomy farther back in time and increasing the chances of spotting PBHs. The NanoGrav project has detected a mysterious signal that could be gravitational waves from black holes smaller than the Sun, which, if confirmed, would strongly suggest PBH activity. Other ambitious projects include LISA, which could detect extreme mass ratio inspirals, where a small black hole spirals into a much larger one, providing another window into PBH existence. The EDGE atomic experiment, still in development, aims to catch mergers of medium-sized black holes, potentially confirming PBHs as seeds of supermassive black holes in the early universe. The Nancy Grace Roman Space Telescope will utilize astrometric lensing, tracking the tiny shifts in star positions caused by passing dark objects. Ground-based facilities like the Vera C. Rubin Observatory will search for fleeting microlensing flashes, mapping compact objects and uncovering unusual candidates that may be PBHs. The Next Generation Very Large Array, or NGVLA, will enhance radio observations, clarifying gravitational wave sources and testing PBH models. Fast radio bursts, mysterious bursts of radio waves, may also reveal lensing effects caused by PBHs. A largely unexplored region of the gamma-ray spectrum, called the MEV band, could help constrain the population of asteroid mass PBHs. Those with masses around 5 times 10 to the power of 19 grams, comparable to a large asteroid, would emit strong gamma rays as they gradually evaporate, producing random bursts across the sky. Wide-field telescopes, highly sensitive even without full sky coverage, could detect these bursts and set limits on their frequency. Not all black holes originate the same way. Some, known as direct collapse black holes, form from massive gas clouds collapsing after the radiation-dominated era, adding another layer of complexity to understanding the universe's earliest structures. The hunt for primordial black holes is a cosmic detective story, with each observation, measurement, and detection method providing a crucial piece of the puzzle. From the tiniest gamma-ray bursts to the ripples of space-time itself, scientists are slowly piecing together the hidden history of these mysterious, ancient remnants of the early universe. But primordial black holes are a different story entirely. Unlike the black holes born from dying stars, these ancient enigmas could have formed in the very first fleeting moments of the universe, within a fraction of a second after the Big Bang. In that chaotic infancy, regions of intense energy and particle density may have collapsed under their own gravity, giving rise to these elusive cosmic objects. As astronomers continue to probe the cosmos with ever more sophisticated instruments and techniques, the tantalizing possibility emerges that we might one day uncover whether these primordial black holes truly exist, and if so, what secrets they guard about the birth of the universe itself. A stellar black hole, sometimes called a stellar mass black hole, begins its life in a far more dramatic and violent fashion. When a massive star exhausts its nuclear fuel, it can no longer support itself against the relentless pull of its own gravity. This triggers a catastrophic gravitational collapse, compressing the star's core into an incredibly dense point. The resulting black hole becomes one of the universe's most mysterious and powerful entities. Stellar black holes typically weigh between 5 and several dozen times the mass of our Sun. They are the remnants of giant stars that exploded in a supernova, a dazzlingly violent release of energy that in some cases manifests as brilliant flashes of gamma rays, the universe's most energetic form of light. Because they form through the collapse of a star, stellar black holes are also sometimes referred to as collapsed stars. Physics offers a strikingly elegant way to describe black holes through the no-hair theorem. According to this principle, no matter the complexity of its formation, a black hole can be completely defined by just 3 characteristics: its mass, which measures how much matter it contains, its electric charge, and its angular momentum, which reflects how fast it spins. The spin of a stellar black hole originates from the rotation of its progenitor star, carried forward as the core collapses into a singularity. This transformation from star to black hole is simply a natural stage in a massive star's life cycle. When a star runs out of fuel, gravity dominates, and the core contracts. If the residual core is relatively light, it may stabilize as a white dwarf or a neutron star, both extraordinarily dense, compact objects. In rare, theoretical cases, it could even become a quark star, an exotic body composed of fundamental particles called quarks. However, if the core's mass exceeds a critical threshold known as the Tolman-Oppenheimer-Volkoff limit, no known force can halt the collapse. The star continues shrinking into an infinitely small point where gravity is so extreme that not even light can escape, creating a black hole. In 1939, scientists estimated this limit at around 0. 7 times the mass of the Sun, though later research in 1996 revised it to between 1.5 and 3 times the Sun's mass. The most massive neutron star identified to date, PSR J0740 plus 6620, discovered in September 2019, has a mass of about 2.42 times the Sun's mass. Einstein's theory of general relativity permits black holes of virtually any mass. Yet, smaller black holes require denser matter to form, and in reality, stars cannot collapse into black holes smaller than a few times the mass of the Sun. Any black holes smaller than this would likely be primordial in origin, born shortly after the Big Bang. Until 2016, the heaviest known stellar black hole weighed roughly 15 2/3 times the mass of the Sun. But in September 2015, the first detection of gravitational waves, ripples in spacetime, from the merger of two smaller black holes revealed a newly formed black hole spinning at a mass of about 62 times the Sun's. In June 2020, astronomers announced the discovery of the smallest known stellar black hole at the time, residing in the binary star system 2 mass 05215658 plus 43592. This compact black hole has a mass of just three times that of the Sun and a diameter of only about 19 kilometers, smaller than many cities on Earth. Beyond stellar black holes, evidence points to 2 other classes: intermediate mass black holes, possibly residing in the centers of globular clusters, dense assemblies of stars, and supermassive black holes, titanic entities anchoring the hearts of galaxies, including our Milky Way, boasting masses millions or even billions of times that of the Sun. Stellar black holes can form intimate partnerships with ordinary stars in binary systems. In such arrangements, the black hole can siphon matter from its companion, which accelerates and heats to hundreds of millions of degrees, emitting X-rays that astronomers detect with specialized telescopes. The companion star can still be observed with standard optical instruments. Distinguishing between neutron stars and black holes can be challenging because both emit comparable energy levels. Scientists use mass measurements to differentiate them. All known neutron stars weigh less than 3 times the Sun's mass, so any compact object exceeding this threshold that does not behave like a neutron star is almost certainly a black hole. While much of our understanding of stellar black holes arises from theoretical physics combined with observational evidence, no one has ever witnessed one directly. A definitive observation would involve tracking a particle or cloud of gas spiraling into the black hole and vanishing from sight. Some binary systems are found far above or below the galactic plane, displaced by so-called natal kicks, powerful thrusts generated during a black hole's formation. Intriguingly, these kicks can propel black holes at speeds comparable to neutron stars, despite their far greater mass, likely due to asymmetrically ejected matter falling back and boosting the black hole's momentum. Certain stellar evolution models suggest that black holes cannot form directly within specific mass ranges, known as the lower and upper mass gaps. The lower gap includes black holes weighing between 2 and 5 times the mass of the Sun, while the upper gap spans roughly 50 to 150 times the Sun's mass, with some estimates narrowing it to 52 to 133 solar masses. The upper mass limit for stars today is believed to be around 150 times the Sun's mass. The scarcity of black holes just above the maximum neutron star mass likely explains the lower mass gap, offering astronomers clues about the complex processes governing the life and death of massive stars. However, the concept of this mysterious gap in black hole masses remains uncertain, and astronomers are still piecing together how it might have formed. Some black holes in this unusual range may not originate from the conventional collapse of massive stars. Instead, they could emerge from the violent merging of 2 neutron stars, creating a new type of black hole that defies traditional formation paths. The LIGO-Virgo collaboration, a global network of gravitational wave observatories, has already detected 3 events where the masses of the merging components fall squarely within this lower mass gap. In addition, astronomers have observed a large, rapidly spinning star locked in a binary system with an invisible companion. This unseen partner emits no detectable light, not even X-rays, yet its gravitational influence suggests a mass approximately 3.33 times that of the Sun. This finding hints at the existence of many low-mass black holes that currently evade detection, lying dormant and invisible because they are not actively accreting matter, which would otherwise produce X-ray emissions observable by conventional telescopes. The upper mass gap, in contrast, emerges from detailed models of stellar evolution. According to these models, stars of extraordinary mass, supermassive stars, undergo a phenomenon known as a pair instability supernova. In this dramatic event, collisions between atomic nuclei and gamma rays drain pressure from the star's core, leaving it unable to resist the relentless pull of gravity. The core partially collapses and triggers an immense explosion, tearing the star apart completely and leaving no remnant behind. This explosive fate is reserved for stars with masses roughly between 130 and 250 times that of the Sun, provided they contain few elements heavier than hydrogen and helium, a condition common in the universe's first generation of stars, known as population 3 stars. Some theoretical models suggest that the upper mass gap may extend downward, potentially starting at 45 times the mass of the Sun, due to a phenomenon called pair instability pulsational mass loss, which occurs just before a star goes supernova. In non-rotating stars, this lower boundary might reach as high as 60 times the Sun's mass. There is also speculation that stars with extremely massive cores, exceeding roughly 133 times the mass of the Sun, might collapse directly into black holes without undergoing a conventional supernova, leaving no observable remnant. This implies that the lower edge of the upper mass gap might indeed mark a fundamental threshold for black hole formation. Past observations, such as those of the LB1 star system, initially suggested a black hole weighing about 70 times the Sun, seemingly outside the predicted upper mass gap, though subsequent studies have challenged this claim. Black holes can also appear in these gaps through processes like the merger of two smaller black holes. Within our own Milky Way, astronomers have identified several stellar mass black hole candidates much closer than the supermassive black hole at the galaxy's core. Most are part of X-ray binary systems, where a black hole siphons matter from a companion star, forming a swirling accretion disk. The masses of these black holes range from roughly 3 times the mass of the Sun to over 12 times, offering a glimpse into the diversity of black holes in our galactic neighborhood. Supermassive black holes, however, belong to an entirely different scale. These cosmic titans can weigh hundreds of thousands, millions, or even billions of times more than the Sun. To visualize this, imagine compressing the mass of billions of suns into a space smaller than a galaxy. Their immense gravity creates a region where nothing, not even light, can escape, making black holes appear perfectly black. While they cannot be observed directly, scientists detect their presence by observing the gravitational influence they exert on nearby stars, gas, and light. Evidence now strongly suggests that nearly every large galaxy in the universe harbors a supermassive black hole at its center, including our own Milky Way. At the core of our galaxy lies Sagittarius A Stai, an enigmatic black hole that does not emit light on its own, but can be studied through the energetic radiation produced as gas and dust spiral inward, heating up in the process. This infall of matter generates extraordinary energy and can create intensely bright regions known as active galactic nuclei, or quasars, which shine far brighter than the combined light of all the stars in their host galaxies. Thanks to the Event Horizon Telescope, an international network of powerful observatories, scientists have successfully imaged 2 supermassive black holes, one in the giant galaxy Messier 87 and the other at the center of the Milky Way, Sagittarius A Stai. To earn the designation of supermassive, a black hole must contain at least 100,000 times the mass of the Sun, though many exceed this by far, with some reaching billions of solar masses. Remarkably, these giants are not as dense as one might assume. If their mass were evenly distributed across the space inside the event horizon, a boundary beyond which nothing can return, the average density could be lower than that of water. This is because as the mass of a black hole increases, its radius grows even faster, spreading the mass over an ever larger volume. For instance, a non-spinning, uncharged black hole weighing about 1 billion suns would have an event horizon nearly as wide as the orbit of Uranus, roughly 19 times the distance from Earth to the Sun. Some black holes surpass even the supermassive category, earning the title ultramassive black holes. These cosmic leviathans weigh more than 5 billion suns and include objects at the centers of galaxies such as TON 618, NGC 166, ESO 446, and NGC 4889, ranking among the heaviest black holes ever recorded. Current theories suggest there may be a natural upper limit to black hole growth, likely around 50 billion solar masses. But in the year 2020, a groundbreaking study shook the foundations of what we thought we knew about black holes. Researchers proposed that there could exist cosmic behemoths so colossal that ordinary supermassive black holes would seem almost modest by comparison. These titanic entities, nicknamed stupendously large black holes, or slabs for short, could outweigh our sun by more than 100 billion times. One candidate for such a gargantuan black hole might be lurking at the heart of a distant galaxy cluster known as Phoenix A. The tale of how scientists first stumbled upon these cosmic leviathans is a story filled with wonder, discovery, and human ingenuity. In 1963, an astronomer named Martin Schmidt was observing an enigmatic object labeled 3C2273. Initially, it was thought to be nothing more than a distant star, unremarkable in its brilliance. But Schmidt's careful study of its light spectrum revealed a staggering truth. The object exhibited a dramatic red shift, a signal that it was racing away from Earth at unimaginable speeds. Using Hubble's law to interpret the data, Schmidt realized that this object was billions of light years away, yet it shone with the energy output of hundreds of entire galaxies. Objects like 3C273 became known as quasars, the luminous beacons of the distant universe. By 1964, only 4 such objects had been cataloged, yet each one was extraordinarily bright and remarkably compact, less than 3 light-years across, implying an incredibly powerful engine at their cores. In an attempt to explain these phenomena, scientists Fred Hoyle and W.A. Fowler proposed the concept of supermassive stars in the early 1960s. They imagined stars burning hydrogen at prodigious rates, their masses ranging from 100,000 to 1 billion suns, capable of producing the staggering energy observed in quasars. Yet their theory faced a critical obstacle. Renowned physicist Richard Feynman pointed out that stars of such immense size could not remain stable. They would collapse into black holes unless supported by some unknown force. Fowler later speculated that these stars might undergo cycles of collapse and violent explosion, potentially explaining the observed bursts of energy. By 1972, scientists Anzalati and Fricker utilized early computer models to test these ideas. Their simulations revealed that even when these massive stars burned through their hydrogen fuel, collapse was inevitable. One striking example from their models showed a star with 750,000 solar masses ultimately succumbing to the inexorable pull of gravity, collapsing into a black hole. Meanwhile, in 1964, 2 visionary scientists, Edwin E. Salpeter and Yakov Zeldovich, proposed a radically different explanation for the quasar phenomenon. They suggested that the extraordinary luminosity of these distant objects could result from matter falling into an immensely dense and massive object, what we now understand as a black hole. Their calculations indicated that such an object would need a mass roughly 100 million times that of the Sun to generate the observed energy. In 1969, Donald Lynden Bell added a crucial insight. As matter falls towards such a massive object, it would not plunge directly inward, but instead form a swirling, flattened disk, much like water spiraling down a drain. This disk would slowly funnel matter into what he termed the Schwartz throat, a concept tied to the black hole's event horizon. Lynden Bell also observed that many nearby galaxies had dim centers, suggesting that they might once have been quasars that had since quieted. In 1967, Martin Ryle and Malcolm Longair proposed yet another captivating idea. They hypothesized that the powerful radio waves emanating from distant galaxies could be explained by jets of particles ejected at speeds approaching that of light. By 1973, working with Peter Scheuer, they suggested that these jets might be powered by the compact core of the galaxy, potentially a supermassive black hole. Observations continued to mount. In 1970, Arthur M. Wolf and Jeffrey Burbidge focused on elliptical galaxies, noting that stars near the centers moved far faster than expected. The only plausible explanation was the presence of a vast, unseen mass, potentially a black hole containing 10 billion solar masses, or a cluster of smaller black holes. Further evidence emerged in 1978 when astronomers studying Messier 87 detected a dark, massive object at its core, estimated at 5 billion times the mass of the Sun. Soon, similar discoveries followed in galaxies such as Andromeda in 1984 and the Sombrero Galaxy in 1988. The hunt for supermassive black holes in our own galaxy also advanced. In 1971, Lyndon Bell and Martin Rees speculated that the Milky Way might harbor one at its center. Their prediction was partially confirmed just a few years later, on February 13th and 15th, 1974, when astronomers Bruce Ballack and Robert Brown used a radio telescope in Green Bank to detect a stationary radio source emitting synchrotron radiation. This object, later named Sagittarius A, provided the first compelling clue of a supermassive black hole lurking in the heart of our galaxy. The launch of the Hubble Space Telescope in 1990 revolutionized the study of galaxy centers, providing unprecedented clarity. In 1994, Hubble's faint object spectrograph observed Messier 87 again, revealing gas near the core spinning at roughly 500 kilometers per second around a tiny region. The only explanation was a mass nearly 2.5 billion times that of the Sun, confined to an area smaller than 1/4 of an arcsecond. In 1995, astronomers using the Very Long Baseline Array studied Messier 106 and observed radio waves from water molecules in a spinning disk around a compact object containing 36 million solar masses. The space was so constrained that multiple smaller black holes could not exist there without colliding, confirming the presence of a single supermassive black hole. Around the same time, the galaxy MCG 630-15 revealed another remarkable discovery. X-ray signals, particularly the iron K-alpha emission line, were detected and distorted in a manner that indicated proximity to a black hole, only 3 to 10 times the radius of the event horizon, emphasizing the extreme conditions in these environments. On April 10, 2019, the Event Horizon Telescope team achieved a historic milestone, the first ever image of a black hole, capturing the massive entity at the center of Messier 87, transforming theoretical speculation into observable reality. By March 2020, scientists proposed that additional photon rings might be visible around the black hole, offering new opportunities to probe these cosmic giants. Despite these breakthroughs, the origins of supermassive black holes remain shrouded in mystery. Astronomers understand that they grow by accreting gas, dust, and even smaller black holes. Yet the formation of the very first seed black holes remains a puzzle. Some theories posit that these seeds arose from stellar mass black holes formed by supernovae, gradually amassing material over time. Others suggest direct collapse of massive gas clouds in the early universe into quasi-stars, which then collapsed into black holes with masses roughly 20 times that of the Sun. Additional hypotheses involve dark matter aiding the accumulation of gas into supermassive stars, or the sudden collapse of primordial stars, each around 100,000 times the mass of the Sun, seeding the monsters we observe today. Even now, as telescopes probe deeper into the cosmos and simulations model the early universe, the question of where these extraordinary black holes came from continues to challenge our understanding of the cosmos, pushing the boundaries of human curiosity and imagination. Some rare theories go even further, suggesting that the universe may not have begun with the Big Bang at all, but with an event known as the Big Bounce. If this were true, it opens the extraordinary possibility that some supermassive black holes predate the universe as we know it, existing long before the previous cosmic cycle concluded. In the earliest epochs of the cosmos, enormous clouds of gas drifted silently across the void, suspended not just in space, but across time itself. These clouds consisted of pristine hydrogen and helium, untouched by heavier elements, which scientists refer to as metal-free gas. When these clouds were illuminated by an intense radiation called Lyman-Werner radiation, an unusual phenomenon occurred. Unlike typical gas clouds, which cool and fragment into smaller clumps that give birth to stars, these clouds resisted fragmentation. The radiation prevented them from losing heat and a relentless pull of gravity. The entire cloud collapsed inward, forming a single colossal object. As the collapse progressed, pressures and densities at the core reached mind-boggling extremes, on the order of 10 million grams per cubic centimeter, a density that defies ordinary comprehension. At this critical juncture, the object could no longer sustain itself. It did not ignite as a star or even as a transient quasi-star. Instead, it underwent a direct collapse into a black hole. These extraordinary entities are known as direct collapse black holes, often boasting masses around 100,000 times that of our Sun. In 2022, computer simulations offered fresh insights into the possible formation pathways of the universe's first supermassive black holes. These simulations revealed that rare, turbulent clouds called primordial halos were fed by unusually strong streams of cold gas. The inflow of cold gas prevented premature star formation, allowing gravitational forces to continue compressing matter until the cloud finally collapsed, producing not one but two enormous black holes with masses of 31,000 and 40,000 times that of the Sun. This breakthrough demonstrated that the emergence of early supermassive black holes might arise from ordinary galaxy formation processes in the infant universe. Yet another intriguing possibility exists. Primordial black holes formed mere moments after the Big Bang itself. If they exist, these black holes would have had far more time than others to accrete matter, potentially explaining how some black holes achieve supermassive proportions so quickly. Meanwhile, many black holes are known to form from the deaths of the first generation of stars, with ample observational evidence supporting this pathway. The alternative theories, such as direct collapse and primordial formation, largely rely on computer models and intricate calculations. Creating a supermassive black hole requires a dense, compact region containing vast quantities of matter with minimal rotational motion. Most cosmic matter carries significant angular momentum, which must be redistributed or expelled during accretion. This spinning motion is one of the primary factors slowing black hole growth. Accretion, the process of gas and dust spiraling into a black hole, is both the fastest and most conspicuous way a black hole gains mass. In fact, the majority of a supermassive black hole's growth occurs during periods of rapid, voracious feeding, events that manifest to observers as quasars or active galactic nuclei, radiating intensely from the hearts of galaxies. Observations of the distant universe, which simultaneously peer back in time, reveal that quasars were far more prevalent when the cosmos was young. This indicates that many supermassive black holes had already formed and were actively growing early in cosmic history. Astronomers have identified exceptionally luminous quasars that existed when the universe was less than 1 billion years old, demonstrating that supermassive black holes had already amassed billions of times the mass of our Sun by that epoch, implying their formation began within the earliest massive galaxies. However, black hole growth has limits. Current theoretical models suggest that the maximum mass a black hole can achieve through standard gas accretion is around 50 billion solar masses. Beyond this threshold, the surrounding accretion disk destabilizes, converting gas into stars orbiting the black hole rather than feeding it. Growth deceleration begins around 10 billion solar masses, and beyond this point, accumulating additional mass becomes increasingly difficult. However, in the most extreme and rare circumstances, scientists theorize that a black hole could grow to an almost inconceivable size, reaching up to 270 billion times the mass of our Sun. Achieving such colossal proportions would require the black hole to rotate at a speed tantalizingly close to its absolute physical limit, though the true maximum spin is ever so slightly lower than the theoretical cap. As a black hole approaches this extreme mass, extraordinary effects begin to manifest. The inner edge of the accretion disk, the innermost stable orbit, starts to expand beyond the region where the black hole's own gravity predominates. Once this threshold is crossed, the disk can no longer maintain its structure, and accretion, the primary process by which black holes grow, ceases effectively. Reaching such gargantuan dimensions is exceedingly unlikely in practice. For a black hole to reach 270 billion solar masses, it would need to be spinning consistently in the same direction as the matter spiraling into it. Yet, in the chaotic expanse of space, infalling material rarely follows such a neat pattern. Instead, matter often arrives from random directions in a phenomenon known as chaotic accretion. This constant tug-of-war means that black holes can be alternately spun up and slowed down. Over cosmic timescales, these competing influences generally reduce the black hole's spin more than they increase it. Black holes can also grow by merging with other black holes, but even these dramatic collisions typically reduce the overall spin rather than amplify it. These combined effects make it extremely rare for black holes to surpass roughly 50 billion times the mass of the Sun, particularly if their rotation isn't near maximum. Only in extraordinary cosmic circumstances do black holes approach such limits. Modern observations of ultramassive black holes, often discovered in quasars or at the centers of massive galaxies, reveal objects ranging between 5 billion and 27 billion solar masses. Growth beyond this range through accretion is essentially impossible given the current age of the universe. However, some theoretical models suggest that over unimaginably long timescales, these cosmic leviathans could continue to grow. In the far future, during the slow gravitational collapse of enormous structures called superclusters, black holes might swell to staggering proportions, potentially reaching up to 100 trillion solar masses. Such unimaginable giants would exert a profound influence on their surroundings. The intense gravitational pull of supermassive black holes at galactic centers is thought to power some of the universe's most energetic phenomena, from luminous quasars to hyperactive galaxies. Interestingly, the mass of a galaxy's central black hole often scales with the mass and size of the galaxy itself, though the relationship varies depending on the galaxy type. Scientists have even identified a precise correlation known as the M-sigma relation, linking a black hole's mass to the velocity of stars in the galaxy's central bulge. Faster-moving stars indicate a heavier central black hole. When astronomers describe an active galactic nucleus, or AGN, they are referring to a galaxy's core harboring a supermassive black hole actively accreting matter. This accretion produces enormous amounts of light, making the galactic center extraordinarily luminous. In contrast, our Milky Way's central black hole, Sagittarius A star, is relatively quiet, producing far less light and not qualifying as an AGN. To explain the diversity among AGNs, astronomers proposed a unified model which suggests that observed differences are largely the result of viewing angle and intrinsic brightness. AGNs typically fall into two main categories. One radiates primarily through a thick accretion disk of infalling matter, while the other emits powerful, nearly light-speed jets from the black hole's poles. When galaxies merge, each carrying its own supermassive black hole, the black holes do not remain stationary. Dynamical friction causes them to drift toward the center of the newly formed galaxy. Eventually, they may form a tight binary system, separated by less than 10 parsecs, and if they draw close enough, just 1,000th of a parsec, the emission of gravitational waves forces a final merger into a single massive black hole. This violent union leaves behind a torrent of gravitational waves, sometimes propelling the newly formed black hole at thousands of kilometers per second. In extreme cases, the kick is so powerful that the black hole is ejected entirely from its host galaxy, a phenomenon known as gravitational recoil. Even more complex interactions can occur if a third black hole enters the system during a galactic merger. The three-body interaction, or slingshot recoil, typically ejects the lightest black hole while the remaining pair continues as a binary. The expelled black holes, known as runaway black holes, may leave observable traces such as unusual AGN positions, dual light signatures, or trails of star formation. Some candidate runaway black holes have been identified in galaxies such as H0450-2958 CID42 and near the dwarf galaxy RCP28, where lines of newly formed stars may mark the path of a departing black hole. Black holes are not entirely permanent. Theoretical physicist Stephen Hawking proposed a process now called Hawking radiation, where quantum effects near the event horizon cause black holes to emit infinitesimal amounts of heat energy. Over unimaginably long timescales, this emission leads to gradual evaporation. For instance, a black hole weighing 100 billion suns would require roughly 2.1 times 10 to the power of 100 years to vanish, while a hypothetical black hole with a mass of 100 trillion suns could take 2.1 times 10 to the power of 1,009 years to fully disappear. Observational evidence for black holes also comes from the Doppler effect, familiar on Earth as the shifting pitch of a passing siren. In space, the Doppler effect alters light. Matter moving away from us appears red-shifted, while matter moving toward us appears blue-shifted. Near a black hole, matter orbits at nearly the speed of light, creating extreme asymmetries in brightness. Sections of the orbiting matter moving away appear dimmer, while approaching sections shine more intensely, distorting the appearance of disks or rings. Modern computer-generated images of black holes, including visualizations of Sagittarius A star, account for these distortions, providing scientists and the public with some of the most compelling depictions of these enigmatic giants at the heart of our galaxy. However, our current generation of telescopes, as advanced as they are, still cannot capture the intricate, fine-grained details of the regions immediately surrounding black holes. The extreme conditions there, gravity so intense that even light struggles to escape, remain beyond the reach of direct observation. For now, scientists must rely on sophisticated simulations and models to visualize and understand these cosmic phenomena. Still, there is a wealth of indirect evidence that reveals the extraordinary behavior of matter in these extreme environments. Observations of matter swirling in regions farther from black holes, where gravity is slightly less overwhelming, have proven invaluable. Unlike light itself, this matter often moves at slower speeds, making it easier to track and measure. For instance, water molecules in space can emit highly specific microwave signals known as masers, analogous to lasers, but operating at microwave frequencies rather than visible light. By analyzing these masers in nearby galaxies, astronomers have detected matter moving at extraordinary speeds, obeying the precise motions predicted by Kepler's laws of planetary motion. This Keplerian motion only occurs when enormous masses are confined to extremely compact regions, a phenomenon that can only be explained by black holes or matter on the verge of collapsing into them. In more distant galaxies, astronomers employ another technique, examining the widths of light emissions, called broad spectral lines. These lines provide crucial insights into the movement of gas in close proximity to a black hole's event horizon, the point beyond which nothing can return. One of the most advanced methods, known as reverberation mapping, studies how these light signals fluctuate over time to estimate both the mass of a black hole and, in some cases, the speed at which it spins. Within our own Milky Way galaxy, compelling evidence points to a supermassive black hole residing at the center, approximately 26,000 light-years from our solar system, in a region astronomers call Sagittarius A star. The movements of nearby stars, particularly one named S2, have provided an extraordinary window into this hidden giant. S2 follows a highly elongated, oval-shaped orbit, completing one full loop roughly every 15 years and 2 months. At its closest approach, S2 comes within 17 light hours of the black hole, a distance about 120 times that between Earth and the Sun. By carefully tracking S2's motion, scientists have deduced that the central object contains a mass around 4 million times that of our Sun, yet it fits into a space no larger than 17 light hours across. Another star, S14, helps refine these measurements, showing that the mysterious central mass occupies an even smaller radius, less than 6 1/4 light hours, roughly equivalent to the orbit of Uranus around the Sun. No known object in the universe, other than a black hole, could be so simultaneously massive and compact. Infrared observations of Sagittarius A star reveal even more fascinating phenomena. Bright flares originating from this region indicate glowing plasma, extremely hot charged gas, orbiting at breathtaking speeds, about 30% of the speed of light, in tight circles just outside the event horizon. These flares appear to emanate from a superheated hotspot within the accretion disk, the spinning disk of matter gradually falling into the black hole, seemingly following circular orbits influenced by powerful magnetic fields. On January 5, 2015, NASA recorded an X-ray flare from Sagittarius A star that was 400 times brighter than usual, setting a record. Scientists theorize this may have been caused either by an asteroid being torn apart as it approached the black hole or by magnetic field lines twisting and snapping within the whirling gas. Despite such remarkable observations, Direct proof of supermassive black holes exists in only a select few galaxies. These include our Milky Way, the Andromeda Galaxy M31, its smaller companion M32, and a handful of others beyond our local group, like NGC 4395. In these galaxies, the velocities of stars and gas rise dramatically as one approaches the central region, exactly as expected if an immense object is exerting a gravitational pull. In most other galaxies, this sharp increase in speed is not observed, leaving uncertainty about the presence of a central black hole. Nevertheless, astronomers widely believe that nearly all galaxies harbor a supermassive black hole at their core, based in part on the M-sigma relation, a correlation between the mass of a galaxy's central black hole and the velocities of stars in the surrounding galactic bulge. This relationship, observed in about 10 galaxies with precise measurements, suggests that galaxies and their black holes may grow and evolve together. March 28, 2011, brought an extraordinary event. Astronomers observed a supermassive black hole tearing apart a mid-sized star. The sudden eruption of X-rays and other emissions left no doubt. The star had strayed too close, falling victim to the black hole's overwhelming gravity. The black hole, previously dormant, had a mass around 1 million times that of the Sun. The event produced jets of material blasting outward at nearly the speed of light, known as relativistic outflows, while a substantial portion of the star's material was likely absorbed into the black hole. Observing the gradual fading of this light will help scientists confirm these theories. The Andromeda Galaxy, located approximately 2.5 million light-years from Earth, hosts a central black hole with a staggering mass of about 140 million suns, far surpassing the Milky Way's. An even more colossal black hole resides in the giant galaxy Messier 87, 48 million light-years away, with a mass of around 6 billion and 12 million suns. The largest black hole known within our local cosmic nebula lies in the galaxy NGC 4889 in the Coma Berenices constellation, roughly 336 million light-years away, containing an estimated 21 billion solar masses. Quasars, immensely luminous and distant objects powered by black holes, provide additional insights, though only through indirect methods. Estimating their masses is fraught with uncertainties, yet some cases are extreme. Ton 618 may contain a black hole with about 40.7 billion solar masses, its light traveling from an era when the universe was still young, with a redshift of 2.219. Other massive quasar black holes include APM 08279 plus 5255 with roughly 10 billion suns, and SMSSJ 215728.2136060215.1 with a mass around 34 billion suns, nearly 10,000 times more massive than the Milky Way's central black hole. Some galaxies even host pairs of supermassive black holes at their cores, remnants of galactic mergers. Collisions between these titanic objects would generate immense gravitational waves. A prominent example is the binary system in the galaxy OJ 287, 3.5 billion light-years away, containing the most massive black hole known in such a system, estimated at 18 billion suns. In 2011, a supermassive black hole was discovered in the small galaxy Henize 210, which lacks a traditional bulge, hinting that black holes may have formed before galactic bulges. Another surprise came in 2012 when astronomers identified a black hole in NGC 1277, about 220 million light-years away in the Perseus constellation. This black hole, with an extraordinary mass of roughly 17 billion suns, accounts for nearly 60% of the galaxy's bulge mass, which itself comprises 14% of the galaxy's total stellar mass. This expanding tapestry of observation, measurement, and inference reveals a universe where black holes, these enigmatic engines of gravity, are not mere cosmic curiosities, but central architects in the life and evolution of galaxies, shaping the stars, gas, and very structure of the cosmos around them. However, other studies pointed toward a very different scenario, challenging previous assumptions. According to this research, the black hole might not be as enormous as once believed, with its mass estimated to fall somewhere between 2 billion and 5 billion times the mass of the Sun, the upper end, 5 billion, being the most probable. On February 28, 2013, astronomers achieved a groundbreaking feat by using the newly launched NuSTAR satellite to measure the spin of a supermassive black hole for the first time. The subject of their study was the black hole at the center of the galaxy, NGC 1365, and what they discovered was astonishing. Its event horizon was spinning at a rate approaching the speed of light, defying expectations and offering fresh insights into the extreme physics governing these cosmic giants. Fast forward to September 2014, when data from multiple X-ray telescopes unveiled a surprising find in the ultra-compact galaxy M60-UCD1. Hidden at its core was a black hole with a mass of 20 million times that of the Sun, astonishingly accounting for more than 10% of the galaxy's total mass. This revelation stunned astronomers, as this single black hole was roughly 5 times more massive than the one anchoring the Milky Way, despite M60-UCD1 itself being less than 5/1000ths of the Milky Way's mass. Such findings challenged preconceived notions of galaxy formation and black hole growth, highlighting that even small galaxies can harbor disproportionately massive black holes. Yet not all galaxies contain these supermassive titans. While the absence of such black holes is often attributed to small dwarf galaxies, one anomaly remains particularly perplexing: the supergiant elliptical galaxy 2261 BCG. This colossal galaxy, one of the largest known in the universe, has not shown signs of hosting an active supermassive black hole exceeding 10 billion times the Sun's mass, even though it is over 6 times larger and 1,000 times more massive than the Milky Way. Various studies suggest that if a black hole exists at its center, its mass could range between 6 billion and 10 billion solar masses, leaving open the possibility that it may either be dormant or smaller than previously expected. In December 2017, astronomers reported the discovery of the most distant quasar known at the time, ULS J1342+0928, which hosts the farthest supermassive black hole ever observed, exhibiting a redshift of 7.54, surpassing the previous record set by ULS J1120+0641, with a redshift of 7. The relentless march of discovery continued in February 2020, when astronomers announced a cataclysmic eruption in the Ophiuchus supercluster. This event, the most energetic detected in the universe since the Big Bang, occurred in the galaxy NGC 6338, where nearly 270 million times the mass of the Sun in material was being consumed by its central supermassive black hole, which weighs 7 billion solar masses. This eruption, which lasted approximately 100 million years, released energy 5 million times greater than the most powerful gamma-ray burst ever observed, generating colossal shock waves and high-energy particle jets that carved a cavity spanning 1.5 million light-years across, 10 times the diameter of the Milky Way. In February 2021, astronomers unveiled a remarkably high-resolution image capturing 25,000 active supermassive black holes, representing about 4% of the northern celestial hemisphere. This image, produced using ultra-low radio wavelengths detected by the Low Frequency Array, LOFAR, in Europe, revealed the staggering diversity and abundance of these cosmic behemoths. Black holes manifest in a variety of sizes, and among the most mysterious are the intermediate mass black holes, or IMBHs. With masses ranging from 100 to 100,000 times that of the Sun, IMBHs occupy the middle ground between stellar black holes, formed from the deaths of massive stars, and the truly gargantuan supermassive black holes, which can exceed 1 billion solar masses. Over the years, astronomers have identified several IMBH candidates within the Milky Way and nearby galaxies, though none have been directly observed. Instead, their presence is inferred from subtle clues, such as the motion of surrounding gas clouds or the light emitted from matter swirling in their accretion disks. One of the most thrilling discoveries came on May 21st, 2019, at precisely 3 minutes and 2 seconds past 3 in the morning UTC, when scientists detected gravitational waves from an event designated GW190521. This event marked the collision of 2 black holes, one with 85 solar masses and the other with 65, merging to form a single black hole of 142 solar masses. About 8 solar masses were converted into gravitational waves, rippling through the fabric of space-time. This discovery, officially published on September 2nd, 2020, provided compelling evidence for the existence of intermediate mass black holes. Before this breakthrough, the strongest hints of IMBHs came from low-luminosity active galactic nuclei, faintly glowing galaxies whose peculiar behavior suggested the presence of black holes. In some cases, scientists estimated the black hole mass using reverberation mapping. In the spiral galaxy NGC 4395, located approximately 4 million parsecs away, a black hole weighing around 360,000 solar masses seems to lurk at the center. A comprehensive analysis of roughly 1 million galaxy light spectra from the Sloan Digital Sky Survey revealed a total of 305 potential IMBH candidates, with X-ray emissions detected from 10 of them, reinforcing the likelihood that they indeed harbor intermediate mass black holes. Another potential hiding place for IMBH is ultraluminous X-ray sources, or ULXs, exceptionally bright X-ray regions often found in starburst galaxies like M82. These sources, typically situated near clusters of young stars, are thought to be black holes feeding on their stellar neighbors. Definitive confirmation requires meticulous study of the companion star's motion to reveal the gravitational influence of an IMBH. Astronomers also speculate that IMBHs may reside within globular clusters, dense spherical star groups orbiting galaxies. By carefully tracking the movement of stars near the cluster center, researchers aim to determine if a massive, unseen object is exerting its influence, providing yet another window into the hidden population of intermediate mass black holes scattered throughout the cosmos. However, none of the claimed discoveries have endured the scrutiny of rigorous follow-up studies. One early example is a dense cluster named M31G1, where initial observations hinted at the presence of a massive black hole at its center. Yet closer analysis revealed that the data could be explained just as convincingly without invoking such a gargantuan object. The mystery of intermediate mass black holes, or IMBHs, remains elusive, but gravitational waves may eventually provide the missing evidence. If an IMBH pairs with another black hole or a dense stellar remnant, their mutual orbit would generate ripples in the fabric of space-time, detectable by highly sensitive observatories such as LIGO and Virgo. Astronomers also rely on a mathematical guideline known as the M-sigma relation, which predicts the mass of a black hole based on the motion of stars around it. According to this relation, smaller galaxies with dimmer central regions should harbor black holes weighing between 10,000 and 1 million times the mass of our Sun. The tiniest black hole predicted so far under this rule resides at the core of a galaxy called RG-118, tipping the cosmic scales at around 50,000 solar masses. In November of 2004, a team of astronomers made headlines by claiming to have identified the first intermediate mass black hole within our own Milky Way. This black hole, designated GCIR 30e, weighs roughly 1,300 times the mass of the Sun and lies only 3 light-years from the Milky Way's central giant Sagittarius A. GCIR 13e exists within a cluster of 7 stars, believed to be the remnants of a much larger assembly torn apart by the intense gravitational forces at the galaxy's core. This discovery fueled the hypothesis that supermassive black holes grow by consuming smaller black holes and nearby stars. Yet in 2005, a German research group cast doubt on this conclusion. By studying the motions of stars within the cluster, they suggested that the black hole might not exist at all. If an intermediate mass black hole truly orbits near the Milky Way's center, its presence could theoretically be inferred by observing the disruptions it causes in the trajectories of nearby stars. In January of 2006, another team led by Philip Carrot at the University of Iowa reported a potentially groundbreaking observation. Using NASA's Rossi X-ray Timing Explorer, they detected a repeating signal called a quasi-periodic oscillation from a black hole candidate in galaxy M82, named M82X1. This black hole appears to feed on a red giant star, siphoning its outer layers in a cosmic tug-of-war. However, the broader scientific community remained cautious. The detected signal completed only about 4 cycles, raising the possibility that the pattern was merely random noise rather than a true periodic oscillation. Even if genuine, uncertainty persisted over whether the rhythm originated from the star's orbit or from slower oscillations within the black hole's accretion disk. In 2009, a team led by Shah Farrell uncovered HLX-1, an enigmatic object that fit neatly into the intermediate mass category. Located within the galaxy ESO2 24349, HLX-1 seemed encircled by a compact cluster of stars, resembling a miniature galaxy of its own. Researchers proposed that HLX-1 might be the remnant of a smaller galaxy absorbed during a collision with its larger host, leaving the black hole and its stellar entourage behind. On July 9, 2012, scientists using the CSIRO radio telescope in Australia reported another significant milestone, presenting strong evidence for what they believed was the first unambiguous intermediate mass black hole. 3 years later, in 2015, researchers at Ko University in Japan observed an unusual gas cloud called CO0, 400 to 22, with particles moving at dramatically different speeds. Computer simulations suggested that these motions could best be explained by a black hole roughly 100,000 times the mass of the Sun. Subsequent studies, however, proposed alternative explanations, including shock waves from supernova explosions, leaving the finding tantalizing but inconclusive. In 2017, astronomers thought they had located a black hole of a few thousand solar masses within the globular cluster 47 Tucanae, based on the velocities and directions of pulsars, highly magnetized spinning stars within the cluster. Yet, as more detailed data emerged, no definitive evidence confirmed the presence of a black hole. By 2018, the Ko University team returned with another potential discovery. They observed multiple streams of cold gas orbiting an unseen object near the center of the Milky Way. This object, labeled HCN 0090.044, appeared to possess a mass of approximately 32,000 suns, which, if verified, would make it the third intermediate mass black hole identified in that region. In 2019, scientists captured gravitational waves from a cataclysmic event in which two smaller black holes, weighing 66 and 85 times the Sun's mass respectively, collided and merged. The resulting black hole measured about 142 solar masses, with the remaining 9 suns' worth of mass released as energy in gravitational waves. This event, designated GW190521, offered a vital clue in the search for intermediate mass black holes. In 2020, astronomers identified a candidate black hole, 3XMJ 215022, 4 plus 055108, located in the direction of the Aquarius constellation, approximately 740 million light-years from Earth. This object potentially represents another member of the intermediate mass category. The following year, 2021, saw the discovery of a black hole weighing around 100,000 suns within the globular cluster B023G78 in the Andromeda Galaxy, attracting significant attention after its initial publication as a preprint. In 2023, the globular cluster Messier 4, the closest such cluster to Earth, revealed another unusual finding. Astronomers studying stellar motions detected an extremely massive and compact object at the cluster's center, about 800 times the mass of the Sun. Its density and compactness suggested it could be a black hole, further illustrating the ongoing challenge and intrigue surrounding the search for these cosmic middleweights, intermediate mass black holes. However, they could not entirely dismiss alternative explanations. Perhaps it was a tightly packed cluster of white dwarfs, neutron stars, or ordinary black holes creating the observed effects. Then, on the 10th of July in the year 2024, a new study emerged that captured the imagination of astronomers. This research focused on 7 rapidly moving stars within Omega Centauri, a massive globular cluster. The movements of these stars suggested they might be tracing an invisible orbit around a hidden black hole, a cosmic giant with a mass of at least 8,200 times that of our Sun. Another compelling candidate for an intermediate mass black hole, a mysterious middle ground between stellar remnants and the colossal supermassive black holes found at galactic centers. Now, the puzzle deepens. These intermediate mass black holes are far too massive to form like their smaller siblings, which emerge from the collapse of a single star. Yet they do not reside in the extreme gravitational arenas where supermassive black holes take shape, the centers of large galaxies teeming with fast-moving stars and violent gravitational forces. How then do these enigmatic middleweights come into existence? Scientists have proposed several theories. One suggests that many smaller black holes gradually collide and merge over vast stretches of time, accumulating mass until they reach intermediate proportions. Another theory posits that enormous stars within dense clusters could collide repeatedly, eventually merging into a final colossal star that collapses into an intermediate mass black hole. A more exotic hypothesis argues that these objects could be primordial, born in the chaotic aftermath of the Big Bang itself. Yet another line of speculation considers whether a single star, unimaginably massive, over 260 times the mass of our Sun, could collapse directly into an intermediate mass black hole, possibly after merging with other stars in a young, crowded cluster. Even if such a spectacular event could occur, witnessing it would be extraordinarily rare. Binary black holes, or black hole binaries, form another chapter of this cosmic narrative. They are pairs of black holes locked in a gravitational dance, orbiting each other in the vastness of space. These duos fall into two primary categories. Binary stellar mass black holes emerge either from the collapse of two massive stars that once orbited one another, or from two separate black holes that eventually find themselves drawn together into orbit. Binary supermassive black holes, on the other hand, typically form when entire galaxies collide, their central black holes gradually spiraling toward each other over millions or even billions of years. For decades, proving the existence of binary black holes was nearly impossible. Their inherent invisibility posed a formidable obstacle. They emit no light, leaving only indirect clues. The instruments of the time were simply not sensitive enough to detect them directly. The breakthrough came through gravitational waves, faint ripples in the fabric of space-time itself, predicted by Einstein's theory of general relativity over a century ago. When two black holes collide, they release a torrent of energy, not in light, but as these ripples. By the late 20th and early 21st centuries, binary black holes had become a focal point of astrophysical research, a promising path toward confirming gravitational waves. As black holes orbit each other, they radiate gravitational waves, gradually losing energy. Their orbits shrink, their velocities rise, and they spiral inward in a slow, inexorable waltz known as the in-spiral phase. Eventually, the two black holes collide, merging into a single entity. This merger is followed by the ring-down phase, when the new black hole settles into a stable shape, emitting additional gravitational waves as it smooths out distortions. In the split second before the merger, the black holes can reach unimaginable speeds, and the gravitational waves they release surge to their maximum intensity. The first direct confirmation arrived in September of 2015 when the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected a signal labeled GW15014. Announced publicly in February of 2016, it revealed two black holes, each roughly 30 times the mass of our Sun, merging over 1,300,000,000 light-years away. In the final 20,000th of a second, the collision converted three solar masses of material into pure gravitational energy, releasing power at an astonishing rate of 3.6 times 10 to the power of 49 watts, far exceeding the combined light of all stars in the visible universe. Since then, more stellar mass black hole mergers have been observed, but supermassive binary black holes remain elusive. Astronomers have identified many promising candidates, yet none has been confirmed beyond doubt. These massive pairs are thought to emerge from galactic collisions. Some galaxies, like NGC 6240, show two luminous cores, hinting at two supermassive black holes still separated but slowly converging. Others, such as SDSS J104807, 74 plus 0055435, and EGSD2 J142033, 6525975, exhibit unusual light variations, suggesting closely orbiting black holes. In some cases, the central regions of galaxies emit periodic light patterns, almost like a heartbeat, implying the presence of a black hole duo. Notable examples include OJ287 and J0437 plus 2456, where one supermassive black hole exhibits anomalous motion, possibly due to a companion or even a recent collision that propelled it outward, a phenomenon known as a recoiling black hole. Quasars like PKS 302-102 further hint at dual black holes orbiting with cycles lasting roughly 1,900 days. When two galaxies collide, their central black holes rarely meet head-on. They usually pass each other like two dancers narrowly missing a step unless dynamical friction, a gravitational tug on surrounding stars, gradually slows them down. Over time, the pair loses energy, tightening their orbit to a few parsecs, 1 parsec being slightly more than 3 light-years. Yet by this stage, nearby stars and gas are depleted, leaving little to facilitate further orbital decay. At extremely close separations, just a few thousandths of a parsec, gravitational waves resume dominance, siphoning energy and propelling the black holes toward an inevitable merger, producing a final cosmic ripple that resonates across the universe. Although the exact mechanics remain partially mysterious, scientists are confident that supermassive black holes, the titanic anchors of galaxies, can collide and merge. Astronomers have even spotted a pair seemingly approaching collision in PKS the Thurn-02-102, a system illustrating the final parsec problem, the challenge of understanding how two black holes already separated by roughly 3 light-years close the last gap. Traditional energy loss mechanisms like gravitational waves are insufficient at this scale. Solutions include introducing additional matter, such as stars or gas clouds, which can drain energy from the orbiting pair, or invoking dark matter with self-interacting properties. Rarely, a third supermassive black hole may join the fray through another galactic merger, creating chaotic interactions that enhance energy loss and orbital eccentricity, intensifying gravitational wave emission. The life of a black hole pair begins with the inspiral, a prolonged period in which the duo orbits each other, inching closer over millions or even billions of years, setting the stage for one of the universe's most spectacular and powerful events. At first, the gravitational waves they emit are barely detectable, whispering through the fabric of space because the black holes are still distant companions, circling each other with patient, silent grace. Over time, imperceptibly at first, they lose energy, and their orbit slowly shrinks, an intimate cosmic dance pulling them closer. Nearby stars and cosmic matter sometimes lend a helping hand, tugging at the black holes and siphoning off energy, nudging them into tighter, faster circles. As they close the distance between them, their speed climbs, their orbits tighten, and the gravitational waves surge with growing intensity, stretching and compressing space like a vast, resonant drum. Eventually, they reach a critical threshold known as the innermost stable circular orbit, or ISCO, the final safe path where they can still orbit without plunging toward each other. Beyond this point, there is no turning back. They dive into a rapid, dramatic final embrace, merging into a single entity in a violent, yet elegant collision. In this instant, the gravitational wave signal peaks, releasing the most powerful echoes of their cosmic ballet. After the merger, the newly formed black hole trembles like a struck bell, reverberating in space and time. This stage, called the ringdown, is when the black hole settles into its final form, the ripples of its vibrations propagating outward as fading gravitational waves. Much of this energy disappears into the black hole itself, while a fraction escapes, quieting gradually, like distant echoes fading into silence. This all occurs within a region called the photon sphere, a bizarre zone where even light can circle endlessly around the black hole, caught in gravity's unyielding grip. A landmark moment arrived on the 14th of September, 2015, when scientists operating the LIGO detector, short for Laser Interferometer Gravitational Wave Observatory, witnessed a black hole merger for the first time. The black holes involved were staggering in size, one 36 times the mass of our Sun, the other 29. Upon merging, they formed a single black hole weighing 62 solar masses. Nearly 3 suns worth of mass vanished, transformed into pure energy, released as gravitational waves in the briefest fraction of a second. At its apex, the energy discharge reached 3.6 times 10 to the power of 56 ergs per second, an unfathomable power, over 200 times the mass of the sun converted into energy every second, roughly 50 times the combined light output of all the stars in the observable universe. The merger itself had occurred between 600 million and 1.8 billion years ago, some 440 megaparsecs from Earth, roughly 1.4 billion light-years distant. The signal matched Einstein's predictions of general relativity perfectly, a resounding confirmation of the theory's accuracy. To understand these cosmic dances, scientists employ sophisticated mathematics. During the early in-spiral, when black holes are distant, they use post-Newtonian approximations, a method that builds on Newtonian gravity while incrementally adding corrections from relativity. Depending on the complexity, these approximations are labeled second order, 2.5 order, or third order. Another approach, called the effective one-body or EOB method, simplifies the two-body problem into a single object moving through a special type of warped space. This is especially useful when one black hole is significantly smaller than its partner, spiraling inward with relentless precision. Following the merger, during ringdown, scientists turn to black hole perturbation theory, calculating how the new black hole oscillates and settles. Most of these final black holes are Kerr black holes, spinning rapidly, their vibrations producing a spectrum of gravitational wave frequencies. Understanding the full journey from in-spiral to merger to ringdown requires solving Einstein's complex equations of general relativity, a task far too intricate for hand calculation. Powerful computers execute numerical relativity, modeling space and time digitally, tracking the black hole's approach, collision, and eventual unification. Precision is critical. Simulations must capture the intense gravitational dynamics near the black holes, while extending far enough to track the gravitational waves radiating into the cosmos. Specialized coordinate systems like Boyer-Lindquist or fisheye coordinates focus computational resources where they are needed most, optimizing these massive simulations. Numerical relativity has evolved dramatically since the first attempts in the 1960s and 70s, when computers and mathematics were insufficient to model the full black hole journey. In 2005, 3 independent research teams revolutionized the field, successfully simulating the entire process: in-spiral, merger, and ringdown. Simulations often combine multiple methods, each optimized for a specific stage of the black hole's evolution. One notable project, the Lazarus Project, pioneered techniques to seamlessly connect these stages at the moment of merger using a space-like hypersurface. These simulations reveal countless details. They calculate the binding energy holding black holes in orbit, the point where orbits become unstable, and the shape and strength of gravitational waves critical for detection. Deep within each other's gravitational field, waves twist and echo, forming a post-Newtonian tail, a resonance stretching backward and forward in time. In the ringdown, the final black hole's spin creates frame-dragging effects, producing gravitational waves aligned with its event horizon. Non-spinning Schwarzschild black holes, by contrast, produce waves that gradually fade, echoes of the in-spiral. Energy lost during the merger is analyzed through the radiation reaction force, simplified by methods like payday resumation, while the chi-characteristic extraction technique, or CCE, estimates energy radiated into space without simulating vast distances. Determining the final black hole's mass and spin is complex in general relativity, influenced by how gravitational waves carry away components of the original spin. By combining waveform segments with the news function, scientists track these effects over time. The event horizon's shape during a merger is another profound mystery. Simulations deploy virtual test particles to map whether they fall into the black hole or escape. As the black holes near each other, their horizons stretch toward one another, forming shapes reminiscent of duckbills. These extensions thin and lengthen, touch and evolve into a narrow bridge, eventually forming a stable connection. By 2011, no simulation had produced an event horizon shaped like a ring, a toroidal topology confirming that the merger process unfolds with distinct and measurable geometry, a silent choreography written in the language of space-time itself. However, some scientists theorize that the universe might hold scenarios far stranger than our imagination, where multiple black holes orbit one another in a cosmic dance, eventually colliding and merging simultaneously. In these extraordinary events, the aftermath produces more than just a single, larger black hole. The gravitational waves generated during these mergers carry momentum away from the system, and to conserve momentum, the newborn black hole receives a powerful recoil, or kick, propelling it through space. This phenomenon seems to defy Isaac Newton's third law at first glance, yet it is a natural consequence of Einstein's general relativity. These kicks can be astonishingly fast, exceeding 1,000 kilometers per second. In rare, perfectly orchestrated conditions, when two black holes of identical mass and spin align precisely, either opposite or along the orbital plane, the recoil can reach nearly 5,000 kilometers per second, enough to eject the black hole entirely from its host galaxy. Most black hole binaries, however, are not so perfectly aligned, and their kicks are usually smaller, ranging from a few hundred kilometers per second. Even so, such speeds are sufficient to expel black holes from dense stellar clusters, preventing further mergers and reducing the number of gravitational waves detectable across the cosmos. For non-spinning black holes, the largest observed kick is around 175 kilometers per second, occurring when one black hole is 5 times the mass of its partner. Scientists carefully study the timing of mergers, mass ratios, spin orientations, and the energy radiated as gravitational waves to understand these cosmic slingshots. In head-on collisions, up to 2% of the total energy can be emitted as gravitational waves. One candidate for a supermassive black hole ejected in this manner is the enigmatic object CXO JAVE272 plus 62591, hinting at the universe's untamed gravitational forces. In 1974, the brilliant physicist Stephen Hawking proposed an idea that reshaped our understanding of black holes. Previously thought to be inescapable voids, black holes, according to Hawking, could emit a faint glow known as Hawking radiation. This radiation originates just outside the event horizon, the invisible boundary beyond which nothing can return. Hawking's insight contradicted earlier assumptions, which claimed that once radiation or matter crossed the event horizon, it was lost forever. Drawing on quantum mechanics, Hawking showed that tiny particle interactions near the black hole's edge could allow energy to escape, a concept that was revolutionary. Though this radiation is extraordinarily weak, beyond the reach of even the most powerful telescopes, it has profound implications over vast stretches of time. Hawking radiation gradually reduces a black hole's mass and rotational energy. Without a continuous influx of matter, a black hole will slowly evaporate, eventually disappearing entirely. For most black holes, this process takes longer than the age of the universe. Interestingly, smaller black holes radiate faster because their Hawking temperature is higher. Hypothetical primordial black holes formed shortly after the Big Bang could lose mass rapidly and vanish in a spectacular burst of high-energy radiation. Although no such event has yet been observed, the search continues. The concept of black holes has captivated scientists for over a century. Predicted by Einstein's theory of general relativity in 1915, their existence was supported by observational evidence only decades later. Black holes are remarkable for their extreme density and gravitational pull, small in size but immense in influence. Early studies by physicists such as Carl Schwarzschild and John Wheeler portrayed black holes as simple, structureless objects with no entropy. Formed when vast amounts of matter or energy collapse into a tiny region, black holes warp spacetime so intensely that not even light can escape. The event horizon marks the boundary of no return. According to relativity, space itself can flow inward faster than light near a black hole, meaning that beyond the event horizon, escape is impossible. Inside, matter is crushed toward a singularity, a point where gravity and space-time curvature become infinite, leaving no physical substance behind. A non-rotating, uncharged black hole is defined only by its mass and event horizon size. The story of black holes evolved further in the early 1970s. Soviet scientists Yakov Zeldovich and Alexei Starobinsky suggested that spinning black holes might emit particles, analogous to how rotating metal spheres can generate electromagnetic energy. In 1972, physicist Jacob Bekenstein proposed that black holes possess entropy proportional to their surface area. Initially skeptical, Hawking revised his stance after discussions with Zeldovich, ultimately combining Bekenstein's insights with quantum theory and general relativity. In 1974, he published a groundbreaking paper demonstrating that black holes radiate energy like hot objects, a process now called Bekenstein-Hawking radiation. Though not yet observed directly, it bridges the quantum world with the intense gravitational forces of black holes, revealing that even these darkest objects are not entirely silent. Hawking radiation begins with vacuum fluctuations, tiny bursts of energy that spontaneously appear and vanish in empty space. These fluctuations can produce particle pairs, one just outside and one just inside the event horizon. The inner particle falls into the black hole, while the outer escapes, becoming Hawking radiation. This process is linked to the Unruh effect and the equivalence principle, which equates being near a black hole's edge to accelerating rapidly in space. An observer hovering near the event horizon would perceive a warm bath of particles, as if space itself were glowing. While many particles fall back into the black hole, some escape, streaming into space as Hawking radiation that, in theory, could one day be detected across the cosmos. The black hole itself functions almost like a cosmic stage, a vast backdrop on which countless quantum dramas unfold. In the language of modern physics, we employ quantum field theory to map out the behavior of particles, a framework that relies critically on defining precise conditions near the black hole's boundary. Once these conditions are established, we can begin to predict the intricate ballet of particles just outside the black hole's gravitational grip. The event horizon, that seemingly formidable edge, is not a solid barrier. Matter and radiation can cross inward, yet nothing escapes outward past this threshold. For an observer positioned near this boundary, gravity would manifest as an invisible, relentless force, akin to the sensation of accelerating through empty space at tremendous speed. At the same time, this observer would sense an almost tangible heat, a consequence of space itself vibrating with energy. As one drifts further from the black hole, this gravitational force diminishes and the perceived heat cools, a phenomenon known as gravitational redshift. Energy, including thermal energy, stretches and weakens as it fights its way out of the black hole's intense pull. Now consider the staggering efficiency of black holes in concentrating matter into infinitesimally small volumes. This efficiency results in the highest known entropy, a measure of disorder or information content within the universe. Scientists speculate that all the information contained inside a black hole may not reside in its volume, but rather encoded on its surface, much like a cosmic hologram. Yet the story grows even more fascinating. Through the mechanism of Hawking radiation, particles gradually escape the black hole, carrying energy away. Einstein's iconic equation, E=mc², reveals that as energy leaks out, the black hole loses mass. This slow attrition is termed black hole evaporation, and over vast epochs, a black hole may vanish entirely. The timescale for this disappearance is tied directly to its initial mass. Specifically, evaporation timescales roughly with the cube of the starting mass. Physicist Stephen Hawking estimated that black holes formed in the universe's infancy, with masses less than about 1 trillion kilograms, 1 followed by 12 zeros, would already have evaporated entirely. In 1976, physicist Don Page refined these predictions, calculating the energy emission rate and the time required for a black hole's entropy or event horizon to be halved, a span now known as the Page time. Reality is more nuanced, for black holes are not perfect absorbers of radiation. Their ability to absorb or emit energy varies depending on particle type, spin, and frequency. For wavelengths similar to the black hole's size, these effects grow increasingly complex. Initially, Page surmised that only black holes with starting masses around 400 billion kilograms or greater could persist until today. However, his assumptions about neutrinos, then thought massless and limited to 2 types, proved incomplete. Modern physics acknowledges 3 neutrino flavors, all with mass, leading to updated calculations. A study in 2008, leveraging contemporary particle physics and cosmic age estimates from the WMAP telescope, refined the threshold for the smallest black hole still extant. Earlier, pre-1998 calculations, built on outdated models, suggested a sun-mass black hole would require roughly 10 to the power of 64 years to evaporate, a span with 64 zeros dwarfing the universe's current age. Supermassive black holes, weighing roughly 100 billion times the sun's mass, would persist for about 2 times 10 to the power of 100 years. The giants formed from collapsing galaxy clusters, tipping the scales at up to 100 trillion solar masses, could take as long as 2 times 10 to the power of 1006 years to vanish completely. These calculations illuminate not just the staggering scale of black holes, but the almost unimaginable expanses of time over which the cosmos evolves, where even the most colossal monsters of gravity gradually yield to the slow, inexorable processes of quantum physics. However, after the year 1998, advances in science and a deeper understanding of the universe caused those numbers to shift slightly. Today, the estimated lifetime of a black hole with the mass of our sun is closer to 10 to the power of 67 years, an almost incomprehensibly long span. When we consider the energy a black hole emits as Hawking radiation, the calculations start with the simplest possible kind of black hole, one that spins not at all and carries no electric charge. This idealized form, called a Schwarzschild black hole, depends entirely on a single property, its mass, often labeled as m. To estimate the amount of energy such a black hole radiates, scientists weave together several essential formulas. One determines the Schwarzschild radius, the black hole's size. Another, the Stefan-Boltzmann law, describes radiation from hot objects. A separate equation defines the black hole's temperature, while yet another calculates the surface area of a sphere, since the black hole's event horizon behaves like a spherical shell. When these pieces are combined, they create a coherent picture of the radiation emitted. One key outcome of this process is the Bekenstein-Hawking luminosity, a term describing how bright the black hole would be if it emitted only photons, particles of light, assuming all radiation comes solely from the event horizon. But the universe already bathes us in a faint glow, known as the cosmic microwave background, with a temperature around 2.7 Kelvin, just slightly above absolute zero. For a black hole to actually shed energy and evaporate, its temperature must surpass this ambient radiation. Calculations show this happens only if the black hole's mass is smaller than about 0.8% of Earth's mass, roughly equal to that of our moon. The significance of black hole evaporation is profound. It reshapes our understanding of these enigmatic objects, linking them to the larger framework of thermodynamics, the science of heat and energy. Black holes are not inert cosmic vacuum cleaners. They exhibit thermal behavior similar to stars or molten metal. Intriguingly, unlike most objects, a black hole heats up as it loses mass. Its evaporation accelerates its temperature rise, following an exponential curve that ends in a dramatic finale. In its last moments, the black hole could explode in a torrent of gamma rays, the universe's most energetic light. As it contracts to near the Planck scale, reaching a size of just 2 Planck lengths, conventional physics ceases to apply, and a theory of quantum gravity becomes necessary. Even stranger phenomena emerge in these models. The evaporation process leads to the black hole information paradox, a dilemma in which all information about matter swallowed by the black hole seems to vanish, defying the principle that information is conserved in the universe. Some theorists suggest Hawking radiation may subtly encode the lost data scrambled beyond recognition. Others propose a tiny remnant particle could preserve this information, while some even consider the possibility that extreme conditions might allow information to disappear entirely. Another puzzle is the trans-Planckian problem. Hawking's original model involved particles near the event horizon with wavelengths smaller than the Planck length, a scale at which known laws of physics break down. This arises because, from an external viewpoint, time appears to freeze at the horizon. A photon emitted with ordinary frequency, when traced backward to its origin, would appear to have init frequency at the horizon. A related phenomenon, the Unruh effect, shows that light waves change frequency depending on motion near a black hole. Staying stationary requires constant acceleration, shifting the detected radiation due to Doppler effects. Tracing a single photon of Hawking radiation back in time, its frequency skyrockets as it approaches the horizon, while its wavelength shrinks to near zero, smaller than any scale physics can currently describe. In the maximally extended Schwarzschild solution, the photon behaves normally only if traced to a region of space predating the black hole, unreachable by any observer. Hawking's more practical model assumes the black hole forms at a specific past moment, with quantum fluctuations at that instant, generating all subsequent radiation. These fluctuations, starting extremely close to the horizon, stretch over time, redshifting into ultra-short wavelengths far beyond current theoretical comprehension. The trans-Planckian problem remains a contentious topic, with many physicists considering it primarily a mathematical artifact of calculations at black hole horizons. White holes, the theoretical opposites of black holes, display similar extremes. Matter falling toward a white hole accumulates at its surface, squeezed into regions where standard physical laws collapse, producing trans-Planckian frequencies from the perspective of an outside observer. To understand these phenomena, physicists often switch to alternative coordinate systems that smooth out the horizon, revealing the processes more clearly. New approaches continue to emerge, especially in understanding Hawking radiation. The Unruh effect, validated through established physics, demonstrates that acceleration through empty space produces detectable warmth, suggesting methods to resolve the trans-Planckian problem. These ongoing studies hint that, despite the current limits of our models, the universe's most extreme objects might still be grasped through careful mathematical and conceptual frameworks. However, the formulas physicists use to describe these extreme effects only hold true if gravity behaves normally at unimaginably tiny scales, all the way down to the Planck scale. This is a realm far smaller than anything we encounter in daily life, a world where distances are measured in fractions of a proton. Consider a black hole lighter than the Planck mass, which is roughly 10 to the power of -8 kilograms. Calculations suggest such a black hole would vanish in a time shorter than the Planck time, about 10 to the power of -43 seconds. These predictions defy common sense and physical reality, leading many researchers to propose that the Planck mass represents the smallest possible mass for a black hole. Yet, in theories that include large extra dimensions, this picture shifts dramatically. Imagine a universe with not just the 3 spatial dimensions we navigate daily and one of time, but 10 or even 11 dimensions. In such frameworks, the fundamental constants of physics, including the Planck constants, could differ significantly from what we observe, demanding adjustments to formulas for phenomena like Hawking radiation. If a tiny black hole has a radius smaller than these extra dimensions, its lifetime would follow entirely new rules, as outlined in scientific studies by Chung in 2002 and Carr in 2005. To probe the intricate workings of black holes more deeply, scientists turn to loop quantum gravity, a theoretical approach that does not automatically replicate the famous formula for black hole entropy discovered by Jacob Bekenstein and Stephen Hawking, unless a certain tunable number within the theory is set precisely. Even so, this framework enables physicists to explore novel quantum gravitational effects on black hole entropy and radiation. When examining the minute fluctuations in a black hole's surface area due to quantum effects, researchers find that a quantum black hole would not radiate energy in a smooth, continuous fashion. Instead, it would emit radiation at sharply defined frequencies, akin to musical notes, layered on top of the conventional Hawking radiation. These discrete signals might one day be detectable if we observe X-rays from evaporating primordial black holes, ancient remnants from the universe's earliest moments. In June 2008, NASA launched the Fermi Space Telescope to hunt for intense bursts of gamma rays that might originate from these tiny black holes as they evaporate. By January 1st, 2024, no such signals had been detected. Should the hypotheses about large extra dimensions prove accurate, facilities like CERN's Large Hadron Collider could theoretically create numerous micro black holes in the laboratory and witness their evaporation. However, none have been observed, and under real-world laboratory conditions, the effects of Hawking radiation remain far too subtle to measure directly. Scientists have devised creative alternatives using analog black holes, systems where fluids simulate gravitational effects. In sonic black holes, for instance, sound waves behave like light near a real black hole, while the flow of an almost perfect fluid mimics gravitational pull. Experiments with Bose-Einstein condensates, a special state of matter at near absolute zero temperatures, have even reported signs of Hawking-like radiation. In September 2010, a laboratory experiment produced an artificial white hole, a region impenetrable to light, claiming to generate light waves analogous to Hawking radiation. These results remain unconfirmed, sparking ongoing debate in the scientific community. Within Einstein's theory of general relativity, a specific mathematical solution called the Schwarzschild metric describes gravity around perfectly round, non-spinning, uncharged objects, unaffected by the universe's overall expansion. This solution, discovered by German physicist Karl Schwarzschild in 1916, provides a practical framework for understanding stars, planets, and even our own Earth and Sun. According to a principle known as Birkhoff's theorem, the Schwarzschild metric represents the most general description for a vacuum surrounding a spherical mass. When such an object collapses to a point where not even light can escape, it forms a black hole. A black hole with no spin and no charge is termed a Schwarzschild black hole, or a static black hole, and these objects are identical except for their mass. A defining feature of a black hole is its event horizon, an invisible boundary marking the point of no return. Nothing made of matter or light can escape once it passes this threshold. Falling past it initially appears ordinary, but escape becomes impossible, and eventual destruction by intense gravity is inevitable. The radius from the black hole's center to this boundary is known as the Schwarzschild radius, often simply called the black hole's radius. Any spherical, non-spinning, uncharged object compressed within its Schwarzschild radius becomes a black hole. Remarkably, the Schwarzschild solution applies to any mass, meaning that theoretically, black holes could form from virtually any amount of matter under the right conditions. Near a Schwarzschild black hole, space-time warps so dramatically that light itself bends in strange ways. Rays skimming close to the black hole may loop around it multiple times, potentially escaping or being trapped indefinitely. Carl Schwarzschild's breakthrough in 1915, published in January 1916, provided an exact solution to Einstein's field equations shortly after general relativity was unveiled. Tragically, Schwarzschild succumbed to a disease called pemphigus while serving in the German army during World War I. Independently, physicist Johannes Drost arrived at the same solution in 1916 using a simpler approach. Early interpretations of general relativity wrestled with peculiarities in the Schwarzschild solution, especially mathematical singularities, which Schwarzschild originally placed at the coordinate system's center. He introduced the Schwarzschild radial coordinate, a powerful tool for describing the warped space surrounding a black hole. However, his conception of this coordinate differed profoundly from our contemporary understanding. In the early 1920s, the landscape of gravitational physics began to shift as two pioneering scientists, Paul Painlevé in 1921 and Olvar Gullstrand in 1922, independently developed alternative ways to describe the Schwarzschild solution using distinct coordinates. These formulations, now collectively known as the Gullstrand-Painlevé coordinates, achieved a remarkable feat. They removed one of the apparent mathematical singularities that had confounded physicists. Yet despite this achievement, both scientists misinterpreted their results. They believed that their coordinate transformations revealed a flaw in Einstein's theory of general relativity, unaware that they were merely observing the same physical reality from a different mathematical perspective. In 1924, British astronomer Arthur Eddington introduced another transformative coordinate system, today known as the Eddington-Finkelstein coordinates. This approach also eliminated the so-called false singularity, but Eddington himself did not fully grasp the profound implications of his work. It would take another decade before the clarity of this insight truly crystallized. In 1932, Belgian physicist Georges Lemaitre developed a further coordinate transformation, now referred to as the Lemaitre coordinates, which for the first time made it clear that the singularity at the Schwarzschild radius was not a physical phenomenon, but a mathematical artifact resulting from an inadequate choice of coordinates. The narrative continued in 1939 when American physicist Howard Robertson demonstrated that an observer freely falling into a black hole would pass through the event horizon within a finite span of their own proper time, even though, from the perspective of a distant observer, it would appear as if the fall took an infinite duration. This insight helped demystify black holes and provided a more accurate depiction of their behavior. By 1950, physicist John Synge contributed a critical clarification in a seminal paper on black holes. He showed that what many considered a dangerous singularity at the radius r equals r Stalas was merely an illusion produced by the choice of coordinates. Synge likened it to a poorly drawn map where two streets seem to intersect, but when redrawn properly, reveal no collision at all. The radius r equals rs dollar actually represented two distinct horizons or boundaries in spacetime. This realization was independently rediscovered by George Sekaras and Martin Kruskal, who introduced what are now called Kruskal-Sekaras coordinates. Their framework provided a more elegant and comprehensive way to describe the entirety of a black hole's spacetime with a single, consistent coordinate system. Despite these breakthroughs, the significance of these discoveries was initially overlooked. Early publications by Lemaitre and Synge appeared in lesser-known journals, and even luminaries such as Albert Einstein continued to regard the radius r, the radius r, s dollar as a true physical singularity. Synge later returned to the problem, deriving the Kruskal-Sekaras solution from the outset using well-chosen coordinates rather than attempting to correct flawed ones, a meticulous approach that was acknowledged by Subramanian Chandrasekhar in his influential book on black holes. The scientific landscape shifted dramatically in the 1960s with the introduction of advanced mathematical techniques, particularly differential geometry, into general relativity. This allowed physicists to describe spacetime with greater precision and to redefine the Schwarzschild radius r equals r s dal not as a physical singularity, but as an event horizon, an invisible boundary permitting unidirectional passage. Within the Schwarzschild solution, two seemingly problematic points emerge: r equals $0 and r equals rs, where the equations diverge, producing infinite values or divisions by zero. These issues only become physically relevant if they occur inside an actual astrophysical object. For instance, the Sun's radius is approximately 700,000 kilometers, whereas its Schwarzschild radius is only about 3 kilometers. Singularities pose no threat unless a star contracts beyond its natural dimensions. The apparent singularity at r equals rs dal s separates Schwarzschild coordinates into two distinct regions: the outer region, r s dal, encompassing the observable universe around stars and planets, and the inner region, 0r rs dollars, containing the true central singularity but cut off from the outer universe by the event horizon. Schwarzschild coordinates fail to connect these regions directly, giving the illusion of two separate universes. However, the singularity at r all stars is not real, but a coordinate singularity. By adopting alternative coordinates such as Lemaitre, Eddington-Finkelstein, Kruskal-Sekaras, Novikov, or Goldstrand-Painlevé, physicists can describe both the interior and exterior of a black hole in a smooth, continuous framework. In contrast, r equals $0 represents a genuine singularity, where spacetime curvature becomes infinite and the laws of physics collapse. This gravitational singularity cannot be eliminated by changing coordinates. It is an intrinsic feature of spacetime. The Schwarzschild solution can be expressed in various coordinate systems, each illuminating a different facet of gravitational behavior near black holes. One illustrative model, known as Flamm's paraboloid, visualizes the warping of space, though it should not be conflated with the simpler gravity wells often depicted in educational exhibits. Objects cannot physically traverse the paraboloid surface because it exists simultaneously in time. Only hypothetical faster-than-light particles, tachyons, could theoretically move along it, while still experiencing gravitational attraction toward the singularity. Objects such as planets follow complex trajectories in Schwarzschild spacetime, often deviating from Newtonian predictions. Mercury, for example, spends more time near the Sun than classical mechanics would suggest, a mild precursor to the extreme behavior of objects crossing an event horizon, which are irretrievably drawn inward. Certain exotic orbits, such as knife-edge trajectories, allow objects to loop around a black hole multiple times before being ejected, illustrating the intricate dance dictated by Einsteinian gravity. The Schwarzschild spacetime possesses remarkable symmetries, remaining invariant under spatial rotations, reflections, and time shifts, though not under arbitrary spatial translations. This places it within a four-dimensional subgroup of the broader Poincare group, encompassing identity operations, time reversals, spatial inversions, and combined transformations. Within this framework, the Ricci curvature scalar and Ricci curvature tensor vanish, a property that can be explored through an orthonormal basis to understand the behavior of curved spacetime. The geodesic deviation equation then reveals how tidal forces push or pull nearby observers, quantifying the stretching and compression induced by gravity near a black hole.